A black hole the size of a proton could outweigh Mount Everest. A single void in deep space holds 66 billion suns inside its gravity, and the universe you're standing in right now might be nothing more than the interior of something far larger than you were ever meant to comprehend. We thought we understood black holes. We gave them names, measurements, categories. We built equations to describe them and telescopes to photograph them. We turned them into diagrams and documentaries and late-night thought experiments about what happens when you fall past the point of no return. But the more we look, the stranger the picture becomes. Because black holes aren't just one thing. They exist on a spectrum so vast, so incomprehensibly wide, that the smallest and largest examples might as well belong to different realities. Some are smaller than atoms born in the first violent second after the Big Bang. Others are the collapsed hearts of dead stars, 20 times the mass of our sun, drifting silently through the dark. And then there are the giants. Sagittarius A star, the 4 million solar mass predator sitting quietly at the center of our galaxy. M87 star, the 6.5 billion solar mass shadow we photographed for the first time in human history, and Ton 618, 66 billion solar masses. A monster so large it breaks the models we use to explain how black holes grow. But here's the part no one tells you. Black holes might not be endpoints. They might be doorways, boundaries where the rules don't end, they transform. Where information doesn't vanish, it hides. Where reality doesn't collapse, it folds into something we don't have the physics to see yet. This is the story of 7 levels of black holes, and what each one reveals about the universe you think you live in. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Black holes should not be possible. That is the first thing you need to understand. Not that they are strange, not that they are powerful, not that they break our comfortable intuition about how reality works. They should not exist at all. The mathematics that predict them are so violent, so extreme, so profoundly unreasonable that when Albert Einstein first saw the equations, he rejected them, not politely, not with the measured skepticism of a scientist entertaining a new idea. He rejected them outright. He believed the universe had better taste than to allow something like this. He was wrong. In 1915, Einstein published his general theory of relativity, a new way of understanding gravity, not as a force pulling objects together, but as the shape of space and time itself, bent and warped by the presence of mass. The heavier the object, the deeper the dent it makes in the fabric of space-time. A marble rolling past that dent curves toward it. We call that curve gravity. The theory was elegant. It explained things Newton could not, and it worked. Within months, other physicists began exploring what the equations allowed. One of them was a German astronomer named Karl Schwarzschild. He was serving on the Russian front during World War I, solving Einstein's field equations in the trenches between artillery barrages. In early 1916, while recovering from a skin disease that would kill him a few months later, Schwarzschild found an exact solution to Einstein's equations. He asked a simple question: what happens to spacetime around a perfectly spherical, non-rotating mass? The math gave him an answer. If you compressed enough mass into a small enough volume, spacetime would curve so sharply that it would close in on itself. There would be a boundary, a radius, beyond which nothing could escape. Not matter, not light, not information, nothing. He called it the Schwarzschild radius. Today we call it the event horizon. Einstein hated it. He thought the solution was a mathematical curiosity with no connection to the real universe. He published a paper in 1939 arguing that nothing in nature could actually collapse that far. Stars would resist, matter would push back. The universe, he believed, had mechanisms to prevent this kind of pathology. For decades, most physicists agreed with him. Black holes were treated as a footnote, a strange prediction buried in the equations that nobody took seriously, and then astronomers started finding them. Let's be clear about what a black hole actually is, because almost every explanation you have heard is wrong in some important way. A black hole is not a hole, it is not a tunnel, it is not a drain, it is not a vacuum cleaner sitting in space pulling everything nearby into oblivion. If you replaced the sun right now with a black hole of the exact same mass, Earth's orbit would not change. The planets would keep spinning in their lanes. We would all freeze to death in the dark, yes, but gravitationally speaking, nothing would move. The pull would be identical because the mass would be identical. Gravity does not care what shape you are. It cares how much you weigh and how close you are. What makes a black hole different is not how much it weighs, it is how small it is. Take the sun, about 2 × 10⁻30 kilograms of hydrogen and helium, and crush it down into a sphere with a radius of about 3 kilometers, not 3,000, 3, smaller than most mountains. Now the gravity at the surface is no longer gentle, it is apocalyptic. Space-time bends so sharply that light itself cannot climb back out. That boundary, that invisible shell where escape becomes impossible, is the event horizon. It is not a surface. It is not made of anything. It is a point of no return written into the geometry of space-time itself. Cross it and your future no longer contains any trajectory that leads away. Every possible path forward points inward. You can fire your rockets at full thrust in the opposite direction and you will still fall. You can try to send a radio signal back to your friends outside and the signal will fall with you. This is not because the gravity is pulling harder than your engines can push. It is because the structure of space-time inside the horizon no longer permits outward as a direction. Inward has become as inevitable as forward in time. And at the center, the equations say there is a singularity. This is the part where physics gives up. The singularity is not a place, it is not a point, it is a moment. A region where the curvature of space-time becomes infinite and every known law of physics stops making predictions. Density diverges, time stops behaving like time, space stops behaving like space. General relativity, the theory that predicts black holes in the first place, breaks down completely at the singularity. It hands you an answer that says divide by 0 and shrugs. Nobody knows what actually happens there. Some physicists think quantum mechanics will step in and smooth things out. Others think space-time itself becomes grainy or foamy at scales smaller than the Planck length, about 10⁻⁻35 meters. Some think the singularity is a sign that general relativity is incomplete, and that a deeper theory, maybe quantum gravity, maybe something we have not even imagined yet, will replace it with something less catastrophic. The honest answer is we do not know. And we may never know because the event horizon hides the singularity from view. We cannot see it, we cannot measure it, we cannot send a probe through to take notes and report back. Whatever happens at the center of a black hole stays there. What we can measure are the properties of the black hole itself, and this is where things get strange in a different way. In the 1960s and 70s, physicists proved a series of theorems showing that no matter how complicated the star was before it collapsed, no matter what it was made of, how fast it was spinning, whether it had magnetic fields or chemical gradients or turbulence in its core, The black hole it leaves behind is described by exactly 3 numbers: mass, spin, and electric charge. That is it. Everything else is erased. The technical term for this is the no-hair theorem. Black holes have no hair, no distinguishing features, no memory of what they used to be. If you collapsed a star made entirely of hydrogen into a black hole, and then collapsed a different star made of iron into a black hole of the same mass and spin, the 2 black holes would be identical, indistinguishable. You could not tell them apart, no matter how precise your instruments were. All the information about what the star was made of, how it lived, how it died, vanishes behind the event horizon. This bothers physicists. It seems to violate a principle called unitarity, which says information cannot be destroyed in the universe. The debate over what happens to that information is still unresolved. Stephen Hawking spent decades arguing both sides of it. Mass is straightforward. The more massive the black hole, the larger the event horizon. Double the mass and you double the radius. The relationship is linear. Spin is more complicated. Black holes can rotate. In fact, most of them probably do, because the stars they formed from were rotating and angular momentum is conserved during collapse. A spinning black hole drags space-time around with it in a process called frame dragging. Close to the event horizon, space-time itself is rotating so fast that nothing can stay still. There is a region called the ergosphere where even if you are not falling in, you are forced to move in the direction of the black hole's spin. You can still escape from the ergosphere, but you cannot stand still. The fastest known spinning black hole that we have measured is called GRS 1915 plus 105, and it completes more than 1,000 rotations per second. 1,000. It is a stellar mass black hole, only about 10 or 15 times the mass of the Sun, but it is spinning so fast that its event horizon is oblate, flattened at the poles, bulging at the equator. The geometry is so twisted that time near the equator ticks at a different rate than time near the poles. If you could somehow survive near a black hole like that, your head and your feet would age at different speeds depending on which way you were oriented. Electric charge is the third property, but in practice it is almost irrelevant. If a black hole had a significant electric charge, it would attract opposite charges from the surrounding plasma and neutralize almost immediately. The universe is full of loose electrons and ions. A charged black hole would pull them in, cancel its own charge, and go back to being neutral within seconds. So while the math allows for charged black holes, and they have exotic names like Reissner-Nordstrom black holes, nobody expects to find one in nature. The no-hair theorem reduces black holes to 2 numbers that matter: mass and spin. That is the entire description. This simplicity is part of what makes black holes so useful as theoretical objects. You do not need to know the life story of the star that collapsed. You do not need to track 1,000,000 variables. You just need 2 numbers and the equations tell you everything about the space-time around it. But simplicity does not mean predictable, and it does not mean safe. Black holes are invisible. That needs to be said plainly, because the images you have seen, the glowing orange disks and swirling accretion flows, are not pictures of the black holes themselves. They are pictures of the material around the black holes. The event horizon emits nothing. It reflects nothing. It is a perfectly black sphere, or in the case of a spinning black hole, a perfectly black oblate spheroid, sitting in the center of all that light and heat and chaos. If you could somehow turn off all the gas and dust and stars nearby, the black hole would vanish from view completely. You would see the stars behind it, lensed and distorted into rings by the curvature of space-time, but the black hole itself would be a hole in the sky. An absence. We only know black holes exist because of what they do to everything around them. Gas falling toward a black hole speeds up, it heats up, it collides with other gas. Friction turns gravitational potential energy into thermal energy and the gas begins to glow. Close to the event horizon, that gas is moving at a significant fraction of the speed of light, and it is hot enough to emit X-rays. Those X-rays we can detect, we can measure how they flicker, we can track how the gas orbits, and from that we can infer the mass and spin of the invisible object at the center. The first strong candidate for a black hole was discovered in 1964. It was an X-ray source in the constellation Cygnus called Cygnus X1. Astronomers found a blue supergiant star in that region that was wobbling. Something massive and invisible was tugging on it. By measuring the wobble, they calculated that the invisible companion had to weigh at least 10 solar masses, too heavy to be a neutron star. The only remaining option was a black hole. For years, Stephen Hawking had a bet with physicist Kip Thorne over whether Cygnus X1 was really a black hole. Hawking bet against it. He said if black holes turned out not to exist, at least he would win the bet. In 1990 he conceded. The evidence had become overwhelming. Since then, astronomers have found black holes everywhere. Some are a few times the mass of the Sun. Some are millions of times heavier. Some are billions. NASA now maintains catalogs of black hole candidates organized by mass and method of detection. The nearest confirmed black hole is called Gaia BH1, sitting about 1,500 light-years away. That sounds far. It is not. In galactic terms, it is right next door. There are probably millions of black holes scattered through the Milky Way, most of them quiet, most of them invisible, drifting through the dark with nothing nearby to eat. And then there is the other end of the scale, TOE N 618, 66 billion times the mass of the Sun, the most massive black hole we have ever confirmed. Its event horizon has a diameter of roughly 2,600 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. Pluto orbits at about 40 astronomical units. The event horizon of TON 618 stretches more than 30 times farther than Pluto in every direction. You could fit dozens of solar systems inside that boundary and still have room left over. Light itself would take roughly 2 weeks to cross from one side of the event horizon to the other. 2 weeks for a beam of light to traverse a single object. TOE N 618 is not close. It is sitting more than 10 billion light-years away. We are seeing it as it existed when the universe was only about 3 billion years old, less than a quarter of its current age. And at that time, it was already fully grown, already 66 billion solar masses. That should not have been possible. There was not enough time. Black holes grow by eating gas and stars and by merging with other black holes. Both processes take time. The rate at which a black hole can swallow matter is limited by radiation pressure. When gas falls in and heats up, it emits light. That light pushes back on the infalling gas. There is a balance point called the Eddington limit, where the outward push of radiation equals the inward pull of gravity. A black hole feeding at the Eddington limit doubles its mass roughly every 50 million years. Run the numbers, and you cannot grow a 66 billion solar mass black hole starting from a stellar mass seed in 3 billion years. Not even close. Something about the early universe allowed black holes to grow faster than they should have. Maybe they started heavier. Maybe entire clouds of primordial gas collapsed directly into black holes without forming stars first. Maybe black holes in the early universe were feeding well above the Eddington limit because the gas around them was denser and hotter than anything we see today. Maybe the no-hair theorem is hiding something, and black holes carry information about their past that we have not learned to read yet. We do not know. What we do know is that the universe built monsters in its infancy. Monsters that by every reasonable model should not have had time to exist. And those monsters are still out there, still growing, still bending space-time into shapes that make the equations flinch. Black holes were a theory. Then they were a curiosity. Then they were a prediction nobody believed. Now they are infrastructure. They are the engines at the centers of galaxies. They are the signposts marking the deepest wells in space-time. They are the laboratories where gravity becomes so strong that quantum mechanics and general relativity are forced into the same room and told to figure out their differences. And they are, in the most literal sense, unfathomable. You cannot measure the bottom. You cannot see the center. You cannot retrieve what falls in. But we keep looking. We keep measuring. We keep building better telescopes and better equations because black holes are not just objects in the universe. They are questions. What happens when matter collapses past every known limit? What happens to information that crosses the event horizon? What happens at the singularity where the equations break? And if the universe can build something as extreme as Tom 618 in only 3 billion years, what else was happening in that early chaos that we have not even begun to understand? Those questions lead somewhere, and the first place they lead is backward. Not to the black holes we see today, but to the black holes that may have formed in the first moments after the Big Bang, before stars, before galaxies, before anything we would recognize as structure existed at all. Chapter 2: Primordial Puzzles, Birth in the Early Universe. Before there were stars to collapse, before there were galaxies, before there was structure of any kind, the universe may have already been making black holes. This is not speculation in the usual sense. It is not science fiction dressed up in equations. It is a serious prediction that falls directly out of the physics we already know, combined with the conditions we know existed in the first moments after the Big Bang. And if it is true, if primordial black holes actually formed in that ancient chaos, then some of them are still out there right now, drifting through the dark, older than any star, smaller than anything you would recognize as a black hole, and possibly making up a significant fraction of the invisible mass holding galaxies together. They are called primordial black holes. And the reason most people have never heard of them is that we have never confirmed a single one exists. Let's go back to the beginning, not the beginning of black hole physics, the beginning of everything. Roughly 8 billion years ago, the universe began in a state so hot and so dense that our current physics cannot describe it. We call that moment the Big Bang, but the name is misleading. It was not an explosion in space. It was the beginning of space itself. Time, distance, energy, matter, all of it emerged from a state where those words may not have even applied. In the first fraction of a second, something extraordinary happened. The universe expanded faster than light, not through space, but as space. This period is called cosmic inflation, and it lasted somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds. In that impossibly brief window, the universe grew from smaller than an atom to roughly the size of a grapefruit. Then inflation stopped, and the universe transitioned into the slower expansion we still see today. Why did inflation happen? Nobody knows. The leading idea is that a field, something like an energy that filled all of space, was sitting in an unstable high-energy state. When it rolled down to a lower energy state, the energy released drove the expansion. The field is called the inflaton, and we have never detected it. But inflation solves so many problems in cosmology that most physicists believe something like it must have happened. It explains why the universe looks so uniform in every direction. It explains why space is so flat, and it explains where the seeds of structure, the tiny density fluctuations that eventually grew into galaxies, came from in the first place. Those fluctuations are key. During inflation, quantum jitter, the random popping in and out of existence that happens at subatomic scales, was stretched across the universe. Tiny quantum fluctuations became cosmic scale ripples in the density of space. Some regions ended up slightly denser than average. Some regions ended up slightly less dense by a fraction of a percent, maybe less, but that was enough. When inflation ended and the universe began cooling, gravity went to work on those ripples. Dense regions pulled in more matter. Less dense regions emptied out. Over hundreds of millions of years, the dense regions collapsed into the first stars and galaxies. That is the standard story. Now here is the twist. If some of those fluctuations were dense enough, they might not have waited. They might have collapsed immediately, in the first seconds after the Big Bang, before atoms even existed. And if they collapsed far enough, they would have formed black holes, not from stars, not from supernovae, from the raw, overdense regions of the primordial universe itself. This idea was first seriously explored in the 1970s by Stephen Hawking and a Soviet physicist named Yakov Zeldovich. They realized that the early universe, unlike the universe today, was incredibly dense everywhere. The average density of matter in the first second after the Big Bang was high enough that even small fluctuations could tip a region over the edge into gravitational collapse. Normally, pressure resists collapse, gas pushes back. But in the extreme conditions of the early universe, before matter had cooled enough to form stable atoms, the resistance was weaker. A fluctuation that was only slightly denser than its surroundings could collapse directly into a black hole without ever forming a star. The mass of such a black hole would depend on when it formed. The earlier the formation, the smaller the black hole. A primordial black hole that formed in the first microsecond after the Big Bang might weigh as much as an asteroid. One that formed a second later might weigh as much as a small planet. The range is enormous. Primordial black holes could theoretically span from subatomic masses far smaller than a single proton, up to thousands of times the mass of the Sun. That is a spread of more than 40 orders of magnitude. No other class of object in the universe has a possible mass range that wide. But here is the problem. Small primordial black holes do not last. In 1974, Stephen Hawking published one of the most important papers in theoretical physics, showing that black holes are not completely black. Quantum effects near the event horizon allow black holes to emit radiation, now called Hawking radiation. The smaller the black hole, the faster it radiates. A black hole with the mass of a mountain would evaporate in a fraction of a second. A black hole with the mass of the moon would take billions of years. The cutoff for surviving to the present day is somewhere around 10 to the 12th kilograms, roughly the mass of a small asteroid or a large comet. Any primordial black hole lighter than that would have evaporated by now, possibly in a burst of gamma rays. Any primordial black hole heavier than that could still be out there, ancient and invisible, drifting through space with nothing to mark its presence unless something falls in. So how would they have formed? There are three main ideas, and none of them are simple. The first is straightforward overdensity. If a region of space right after the Big Bang happened to be denser than average by more than a critical threshold, it would collapse under its own gravity. The trick is figuring out what could produce fluctuations that strong. The ripples we see in the cosmic microwave background, the faint temperature variations that map the density of the universe 380,000 years after the Big Bang, are only about 1 part in 100,000. that is not enough to form primordial black holes. You would need fluctuations at least 10 or 100 times stronger in localized regions. One possibility is that inflation itself was not perfectly smooth. Maybe the inflaton field had small bumps or kinks that produced stronger fluctuations in certain regions. Maybe there were brief moments during inflation when the expansion slowed or sped up, amplifying the quantum jitter. These are not wild guesses. They are predictions that fall out of specific models of inflation. If those models are right, primordial black holes would be a natural byproduct. The second formation mechanism involves phase transitions. As the universe cooled in the first seconds after the Big Bang, it went through a series of transitions, moments when the fundamental forces separated and the behavior of matter changed. One of these transitions happened when quarks, which had been floating freely in a hot soup, became confined inside protons and neutrons. That transition was not perfectly uniform. Some regions transitioned earlier than others. The boundaries between those regions, called domain walls or bubbles, could have been regions of extreme density. If the density was high enough, the boundaries could have collapsed into black holes. This mechanism is elegant because it does not require unusually large fluctuations. It just requires that the phase transition happened in a lumpy way, which many models predict. The black holes formed this way would have masses tied to the energy scale of the transition. For the quark confinement transition, that mass is roughly in the range of a large asteroid. Different transitions could produce different masses. The third mechanism involves cosmic strings. These are hypothetical one-dimensional defects in space-time, left over from the earliest moments of the universe. Think of them as cracks in the fabric of reality, thinner than a proton but stretched across light years, carrying enormous tension. If cosmic strings exist, and we have never seen one, they would have writhed and intersected in the early universe. When two strings crossed, they could pinch off a loop. That loop would radiate gravitational waves and shrink. If the loop was dense enough and small enough, it could collapse into a black hole before it radiated all its energy away. Cosmic strings sound exotic, and they are, but they appear in many theories of particle physics and cosmology. If the universe went through a period of symmetry breaking in its first moments, which most grand unified theories predict, cosmic strings are a natural consequence, and if cosmic strings formed, primordial black holes from string loops might have formed too. All three mechanisms are speculative. None of them have been confirmed, but they are not fringe ideas. They are serious proposals that appear in refereed journals and are debated at conferences. The point is that the early universe was not a smooth, gentle place. It was violent, chaotic, and extreme. And in that environment, black holes could have formed through channels that have nothing to do with stars. Now the question becomes, how many? If primordial black holes formed, how common are they? Are they rare curiosities, a few scattered through each galaxy, or are they abundant enough to make up a significant fraction of the matter in the universe? This is where the idea gets really interesting, because primordial black holes have been proposed as a candidate for dark matter. Dark matter is the invisible mass that holds galaxies together. We know it is there because galaxies rotate too fast. Stars on the outer edges of a galaxy are moving so quickly that they should fly off into space unless there is more mass pulling them inward than we can see. That extra mass, whatever it is, outweighs all the visible matter in the universe by a factor of 5. We call it dark matter, but we have never directly detected a particle of it. We do not know what it is made of. Dozens of candidates have been proposed. Primordial black holes are one of them. The idea is simple. If enough primordial black holes formed in the early universe, and if they had masses in the right range, they could be the dark matter. They would be invisible because they do not emit light. They would clump together gravitationally because they have mass. And they would not interact with ordinary matter except through gravity, which is exactly what dark matter is observed to do. From a distance, a galaxy filled with primordial black holes would look identical to a galaxy filled with dark matter particles. You could not tell the difference without getting close. But there are problems, big ones. If primordial black holes make up the dark matter, they have to be in a very specific mass range. Too light and they would have evaporated. Too heavy and we would have detected them through their gravitational effects. Astronomers have spent decades looking for black holes by watching how they bend light from distant stars, a technique called gravitational microlensing. When a black hole passes in front of a star, the star briefly brightens as the black hole's gravity focuses its light toward us. By measuring how long the brightening lasts and how much the brightness changes, you can calculate the mass of the object doing the lensing. Surveys have looked at millions of stars and found a handful of microlensing events. Most of them are consistent with ordinary objects, brown dwarfs, dim stars, planets. A few are ambiguous. But the surveys have ruled out large populations of black holes in certain mass ranges. If primordial black holes between about 1/10 and 100 times the mass of the Sun made up most of the dark matter, we would have seen them by now. We have not. That does not mean primordial black holes do not exist. It means they cannot be the dominant form of dark matter in that mass range. The allowed windows are narrower now. Primordial black holes in the asteroid mass range, around 10 to the 12th to 10 to the 17th kilograms, are still viable. So are much heavier ones, above 1,000 solar masses, where the microlensing surveys lose sensitivity. But the window is closing. Every new survey tightens the constraints. If primordial black holes are out there, they are either very light or very heavy or very rare. There is another reason to care about primordial black holes, even if they are not the dark matter. They could be the seeds that grew into the supermassive black holes we see at the centers of galaxies. This brings us back to TOEN 618 and the impossibly early galaxy problem. Supermassive black holes should not have existed in the early universe. There was not enough time for them to grow from stellar mass seeds. But if primordial black holes formed in the first second after the Big Bang, they could have started much heavier. A primordial black hole weighing 100,000 solar masses, sitting at the center of a dense gas cloud in the early universe, could grow to 1 billion solar masses in a few 100 million years. That is still fast, but it is possible. Without primordial black holes, the timeline does not close. Stefano Profumo, a physicist at the University of California, Santa Cruz, has argued that primordial black holes could have acted like cosmic seeds, helping matter clump together earlier than expected. A dense region with a primordial black hole at its center would attract gas and dark matter faster than a region without one. The black hole would not need to grow by eating everything. It would just need to sit there, pulling matter inward, giving the surrounding region a head start on forming a galaxy. If this is right, primordial black holes were not just passengers in the early universe, they were architects. The trouble is we have no direct evidence. We have never seen a primordial black hole. We have never detected Hawking radiation from a small one evaporating. We have never caught one in the act of forming or lensing starlight in a way that definitively rules out other explanations. Everything we know about primordial black holes comes from theory and indirect constraints, but the indirect constraints are getting tighter. Observations of the cosmic microwave background have ruled out large populations of primordial black holes forming in certain ways. If too many black holes formed early, they would have distorted the microwave background in ways we do not see. Gravitational wave detectors like LIGO have opened a new window. Some of the black hole mergers LIGO has detected involve black holes with unusual masses, heavier than expected from stellar collapse, but lighter than the supermassive ones in galaxy centers. A few researchers have suggested these could be primordial black holes colliding billions of years after they formed. The idea is controversial. Most of the LIGO detections are consistent with stellar origin black holes, but the possibility is there. One of the strangest aspects of primordial black holes is that they probe physics at scales we can barely imagine. A black hole that formed in the first microsecond after the Big Bang would carry information about the conditions of the universe at that time. The density, the temperature, the strength of the fluctuations, all of it would be encoded in the black hole's mass and formation history. Finding even a single primordial black hole would be like discovering a fossil from the first second of time. Hawking radiation adds another layer. If small primordial black holes are evaporating right now, they would be emitting gamma rays as they die. The final moments of a black hole's life, when it has radiated away all but a tiny fraction of its mass, are predicted to be violent. The black hole would explode in a burst of high-energy particles. Astronomers have looked for these bursts. So far, they have found nothing definitive. Some gamma-ray sources remain unexplained, but none of them have the signature you would expect from an evaporating black hole. That does not mean it is not happening. It means if it is happening, it is rare or the signal is being drowned out by other sources. The theoretical reviews of primordial black holes emphasize that they remain attractive precisely because they can probe cosmology at times inaccessible by other methods. We cannot build a particle accelerator powerful enough to recreate the conditions of the first microsecond after the Big Bang. We cannot see that far back with telescopes. The cosmic microwave background only shows us the universe at 380,000 years. Everything earlier is hidden. Primordial black holes, if they exist, are direct remnants of that hidden era. They are the only objects in the universe that might have formed before atoms, before light could travel freely, before any of the structures we see today began to take shape. One of the most fascinating aspects of the primordial black hole hypothesis is how it sits at the intersection of so many unsolved problems. Dark matter, supermassive black hole formation, the nature of inflation, the existence of cosmic strings, the validity of Hawking radiation, all of it connects. If primordial black holes exist, they could help answer multiple questions at once. If they do not exist, the constraints we have placed on them still teach us something about the early universe. Either way, the search is not wasted effort. The current state of the field is one of cautious interest. Primordial black holes are not confirmed. They are not mainstream, but they are not dismissed either. The idea has survived decades of scrutiny and remains a viable hypothesis. New observations, better gravitational wave detectors, more sensitive gamma-ray telescopes, deeper microlensing surveys, all of these could tip the balance. We are in a strange moment where the next generation of instruments might either find primordial black holes or rule them out entirely. If they are found, the implications are staggering. It would mean the universe was making black holes before it made stars. It would mean some of the dark matter holding galaxies together is not exotic particles but objects we already understand, just formed in a way we had not imagined. It would mean the monsters at the centers of galaxies did not grow from stellar seeds. They were born heavy in the first moments of existence. And it would mean that Hawking radiation, one of the most beautiful and strange predictions in theoretical physics, is not just math. It is a process happening in the universe right now, quietly evaporating black holes that have been drifting through space since before the first star ignited. If they are ruled out, that tells us something too. It would mean the early universe was smoother than we thought. It would mean the fluctuations from inflation were not strong enough to collapse directly into black holes. It would mean cosmic strings, if they exist, did not produce black holes in large numbers. And it would mean we need to look elsewhere for the dark matter and for the seeds of supermassive black holes. Either answer moves the field forward. For now, primordial black holes remain in a kind of limbo, predicted by theory, allowed by observation, but never seen. They are ghosts of the early universe, if they exist at all, and the search for them continues because the questions they raise are too important to ignore. If the universe could make black holes in its first second, what else was it doing that we have not yet discovered? What other relics of that ancient chaos are still out there, waiting to be found? The story of black holes does not begin with stars. It begins in the first fractions of a second after the Big Bang, in a universe so hot and so dense that the rules we know today had not yet been written. And if that story is right, some of those first black holes are still here, older than galaxies, smaller than mountains, invisible, silent and patient, waiting for us to notice them. But most black holes do not come from the Big Bang. Most of them come from stars, and when a star dies, it does not go quietly. But most black holes do not come from the Big Bang. Most of them come from stars, and when a star dies, it does not go quietly. Stars are not permanent. That needs to be said first, because when you look up at the night sky, the stars look eternal. The same constellations your ancestors saw thousands of years ago hang in the same positions tonight. Polaris has been the North Star for centuries. Orion still hunts across the winter sky. Nothing seems to change, but that stillness is an illusion created by the fact that human lifetimes are absurdly short compared to stellar timescales. Stars live for millions or billions of years. We live for decades. From our perspective, they might as well be frozen in place. They are not. Every star you see is burning. Not burning the way wood burns, but burning in the nuclear sense. Deep in the core, hydrogen atoms are being crushed together under unimaginable pressure and temperature until they fuse into helium. That fusion releases energy, a lot of energy, enough to keep the star shining for millions of years. Enough to generate an outward pressure that balances the inward crush of gravity trying to collapse the star into a point. As long as the fusion continues, the star stays stable. Gravity pulls in, pressure pushes out. The two forces lock into equilibrium and the star just sits there shining. But the fuel does not last forever. A star like our Sun will burn hydrogen in its core for about 10 billion years. More massive stars burn faster and die younger. A star 10 times the mass of the Sun might only last 20 million years. A star 50 times the mass of the Sun could burn through its core hydrogen in less than 5 million years. The bigger the star, the shorter its life. The reason is simple. Massive stars have more gravity squeezing their cores, which means higher temperatures, which means faster fusion. They burn brighter and they burn out faster. When the hydrogen in the core runs out, the star does not die immediately. It adapts. The core contracts. As it contracts, it heats up. Eventually, it gets hot enough to start fusing helium into carbon and oxygen. The star swells into a red giant, or, for the really massive ones, a supergiant. Fusion continues, but now the star is burning a heavier element. Helium does not last as long as hydrogen did. When the helium runs out, the core contracts again, heats up again, and starts fusing carbon, then oxygen, then neon, then magnesium, then silicon. Each stage is shorter than the last. A massive star might spend millions of years burning hydrogen, a million years burning helium, a few thousand years burning carbon, and less than a day burning silicon. By the time the core is fusing silicon into iron, the star is living on borrowed time. Iron is the end of the line. Fusing iron does not release energy, it consumes energy. Once the core is iron, there is no fuel left to burn. The outward pressure supporting the star vanishes, and gravity wins. The collapse happens fast. The core of a massive star, an object roughly the size of Earth weighing more than the Sun, collapses in less than a second. In that second, the core shrinks from thousands of kilometers across to about 20 kilometers. The material is falling inward at nearly a quarter of the speed of light. When the collapse stops, either because the core has become a neutron star or because it has punched through into a black hole, the outer layers of the star are still falling inward. They hit the rebounding core and bounce. That bounce is what we call a supernova. A supernova is not an explosion in the traditional sense, it is a shock wave. The energy released when the core collapses and rebounds tears through the outer layers of the star at thousands of kilometers per second. In a few hours, the star brightens by a factor of 1 billion. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The explosion scatters the outer layers into space, seeding the surrounding gas clouds with all the heavy elements the star spent its life creating. Carbon, oxygen, nitrogen, iron, gold, uranium, everything heavier than helium was made inside a star and scattered by a supernova. Every atom in your body except the hydrogen was forged in a stellar core and blasted into space by a dying star. But we are not here for the outer layers. We are here for what is left behind, the core. If the core is light enough, between about 1.4 and 2 or 3 times the mass of the Sun, it stops collapsing and becomes a neutron star. Neutron stars are their own kind of strange. They are made almost entirely of neutrons packed so tightly that a teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is so strong that if you dropped an object from 1 meter above the ground, it would hit the surface at several million kilometers per hour. Neutron stars spin hundreds of times per second and have magnetic fields trillions of times stronger than Earth's. They are among the most extreme objects in the universe. But if the core is heavier than about 3 solar masses, neutron degeneracy pressure is not enough. There is a limit to how much weight neutrons can support before they give up. That limit is called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who calculated it in the 1930s. The exact value is still debated because it depends on the equation of state for nuclear matter at extreme densities, which we do not fully understand. But the limit is somewhere between 2 and 3 solar masses. Cross that line and nothing can stop the collapse. The core keeps falling. The neutrons are crushed together so tightly that the concept of particles stops meaning much. The density climbs toward infinity. The curvature of space-time becomes so extreme that the core disappears behind an event horizon. A stellar mass black hole is born. The entire process, from the moment the core runs out of fuel to the formation of the black hole, takes less than a minute. 1 minute to end a life that lasted millions of years, and the black hole that emerges weighs only a fraction of what the original star weighed. The rest was scattered into space. A 50 solar mass star might leave behind a black hole of 10 or 15 solar masses. The rest is gone, blown across light years, enriching the galaxy with the raw material for future stars and planets, and eventually people. Stellar mass black holes are the most common kind. There are probably 100 million of them scattered through the Milky Way alone. Most of them are invisible, sitting quietly in the dark with nothing nearby to eat. A black hole without an accretion disk, without a companion star, without gas or dust falling in, produces no light. It is just a knot of curved spacetime drifting through the galaxy like a ghost. We only know they are there when something gets close enough for us to notice. The easiest way to find a stellar black hole is to look for a binary system. Many massive stars are born in pairs, orbiting each other. If one of them dies and becomes a black hole while the other is still shining, the black hole can pull gas off its companion. That gas does not fall straight in. It has angular momentum, so it spirals inward, forming a flat disk called an accretion disk. As the gas spirals closer to the event horizon, it speeds up. It collides with other gas. Friction heats it to millions of degrees. At those temperatures, the disk glows in X-rays. X-ray binaries are the smoking guns of stellar black holes. Astronomers have catalogued dozens of them. One of the first and most famous is Cygnus X1, discovered in the 1960s. Cygnus X1 is a massive blue supergiant star locked in orbit with an invisible companion. The companion weighs about 15 solar masses. The star wobbles as it orbits, pulled by the gravity of something it cannot see. X-rays flicker from the region between them. Every observation points to the same conclusion. The invisible companion is a black hole, and it is eating the supergiant one bite at a time. For decades, Cygnus X1 was the best evidence we had for black holes. It was not definitive. You could not see the event horizon. You could not measure the object directly. You could only infer its existence from the behavior of the matter around it. But the case was strong enough that Stephen Hawking, who had spent years arguing that black holes might not exist, conceded a bet in 1990. He had wagered that Cygnus X1 was not a black hole. He lost. The evidence had become overwhelming. Since then, astronomers have found black holes everywhere. Some are in binaries pulling gas off companions. Some are alone, detected only when they pass in front of a background star and their gravity bends the starlight toward us. That technique, called gravitational microlensing, has revealed isolated black holes drifting through the galaxy with nothing nearby to illuminate them. The nearest confirmed black hole, Gaia BH1, is about 1,500 light-years away. It was discovered because it is orbiting a sun-like star, and the star's motion gave it away. The black hole itself is silent, and then in 2015, everything changed. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. Gravitational waves are ripples in space-time itself, predicted by Einstein but never directly observed until LIGO turned on. The first detection came from two black holes, each about 30 solar masses, spiraling into each other and merging. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. That energy was not released as light, it was released as gravitational waves, stretching and squeezing space-time as they radiated outward at the speed of light. LIGO heard it. Two detectors, one in Louisiana and one in Washington state, felt space-time itself vibrate as the waves passed through Earth. The signal lasted less than a second. The frequency rose as the black holes spiraled closer, then cut off abruptly when they merged. From that brief chirp, physicists calculated the masses of the two black holes, how fast they were spinning, how far away the collision happened, and the mass of the final merged black hole. They could even tell that the merger released 3 solar masses worth of energy as gravitational waves, 3 entire suns converted into ripples in spacetime. Since that first detection, LIGO and its European partner Virgo have detected dozens of black hole mergers. Some involve black holes much heavier than expected. Some involve black holes with unusual spins. A few involve mergers between a black hole and a neutron star. Each detection is a new data point, a new measurement of objects that were invisible until gravitational wave astronomy opened the field. The black holes LIGO detects are fascinating because many of them are heavier than the stellar black holes astronomers expected to find. Stellar evolution models predict that when a massive star collapses, it should leave behind a black hole weighing no more than about 30 or 40 solar masses. Stars heavier than that should lose so much mass to stellar winds during their lives that the core left behind at the end is not heavy enough to form a very massive black hole. But LIGO has detected black holes weighing 50, 60, even 80 solar masses. Some of the mergers involve black holes in a range that stellar evolution says should not exist. There are two possible explanations. The first is that the models are wrong. Maybe massive stars in low metallicity environments, regions of the galaxy where heavy elements are rare, lose less mass than expected. Maybe they hold on to more of their weight and leave behind heavier black holes when they die. The second explanation is more exotic. Maybe some of the black holes LIGO detects are not from stars at all. Maybe they are primordial black holes, formed in the early universe, now colliding billions of years after they were born. The debate is ongoing. Most of the detections are consistent with stellar origins, but a few remain puzzling. Stellar black holes do more than sit quietly in the dark. They shape their surroundings. When a black hole pulls gas off a companion star or sweeps through a dense gas cloud, the accretion disk that forms around it can launch jets. These jets are streams of matter and energy blasted outward at nearly the speed of light, perpendicular to the disk. The mechanism is not fully understood, but it involves the black hole's spin and the magnetic fields threading through the accretion disk. The jets can extend for light years, punching through the surrounding gas and heating it to millions of degrees. Systems with jets are called microquasars. They are smaller versions of the quasars that sit at the centers of galaxies, but they operate on the same principles. Matter spirals inward. Energy is extracted somehow from the rotation of the black hole or the infall of matter. That energy is focused into two narrow beams and fired into space. The jets from a microquasar are not powerful enough to affect the entire galaxy the way a supermassive black hole can, but they can clear out gas in the immediate neighborhood and suppress star formation in nearby clouds. Stellar black holes also play a role in galactic chemical evolution. When a massive star dies in a supernova, it scatters heavy elements into the interstellar medium. Those elements mix with the surrounding gas and become part of the next generation of stars. Every star that forms after the first generation contains traces of the elements forged in earlier stars. The Sun, for example, is a third-generation star. It contains carbon and oxygen and iron created by stars that died billions of years before the solar system formed. Without supernovae, without the deaths of massive stars, there would be no heavy elements, there would be no rocky planets, there would be no chemistry complex enough to support life. Black holes are the final punctuation mark on that process. The heaviest stars, the ones that burn the brightest and die the fastest, are the ones that leave black holes behind. They are also the ones that produce the most heavy elements. Every stellar black hole in the galaxy is a marker, a gravestone for a star that lived fast, burned bright and ended violently, and the gas clouds enriched by those deaths are the nurseries where new stars are born. There is something almost poetic about it. The universe recycles. Stars are born from the ashes of earlier stars. Black holes form from the deaths of the most massive ones. The gas and dust scattered by supernovae collapse into new stars, some of which will themselves die and scatter more material. The cycle has been running for more than 13 billion years, generation after generation, each one slightly richer in heavy elements than the last. We are made of star stuff, to borrow Carl Sagan's phrase. Every atom in your body heavier than hydrogen was created in a stellar core and scattered into space by a supernova, and some of those stars left black holes behind. Stellar black holes are also laboratories for extreme physics. Near the event horizon of a 10 solar mass black hole, space-time is curved so sharply that clocks tick noticeably slower than they do far away. An astronaut falling toward the event horizon would see the rest of the universe speed up. Light from distant stars would blue shift as they fell. If they looked back at a clock on a distant spaceship, they would see it ticking faster and faster as they approached the horizon. Meanwhile, an observer on the distant spaceship watching the astronaut fall would see the astronaut slow down, their clock ticking slower and slower, their image red-shifting and dimming until they faded from view just before crossing the horizon. The astronaut would experience crossing the event horizon as a moment. The outside universe would see them freeze at the edge. This is not science fiction. This is general relativity. Time is not absolute. It is relative, shaped by gravity. Near a black hole, the effects are extreme enough to measure. Satellites orbiting Earth experience time dilation at a level of a few microseconds per day, which GPS systems have to correct for. Near a black hole, the effect is not microseconds, it is seconds, minutes, hours. Time itself becomes a coordinate that depends on where you are and how fast you are moving. Accretion disks around stellar black holes also test our understanding of plasma physics and magnetic fields. The gas in an accretion disk is not falling smoothly. It is turbulent, threaded with magnetic fields that twist and reconnect, heating the gas and generating instabilities. The inner edge of the disk, where the gas is orbiting just outside the event horizon, is moving at a significant fraction of the speed of light. At those speeds, relativistic effects dominate. The gas Doppler shifts. The light is beamed forward in the direction of motion. The disk itself is a laboratory for physics we cannot reproduce on Earth. Stellar black holes are also clocks. When gas spirals into a black hole, it does not fall smoothly, it flickers. The X-rays from an accretion disk vary on timescales ranging from milliseconds to hours. Some of that variability is random, driven by turbulence in the disk. But some of it is periodic. Astronomers have detected quasi-periodic oscillations, flickering patterns that repeat at specific frequencies. The frequency depends on how close the gas is to the black hole and how fast the black hole is spinning. By measuring the oscillations, astronomers can infer the black hole's spin and mass. It is like listening to the black hole ring like a bell. Spin matters because it changes the geometry of spacetime around the black hole. A non-rotating black hole has a simple event horizon. A spinning black hole drags spacetime around with it, creating a region called the ergosphere where nothing can stand still. Inside the ergosphere, spacetime itself is rotating. If you tried to hover in place, you would be dragged around the black hole whether you liked it or not. The faster the black hole spins, the larger the ergosphere and the more twisted the spacetime becomes. The fastest spinning stellar black hole ever measured is called GRS 1915 plus 105. It is spinning at about 98% of the maximum speed allowed by general relativity. Any faster, and the event horizon would disappear, exposing the singularity. The laws of physics, as we understand them, do not permit that. The maximum spin is set by the point where the centrifugal force at the event horizon exactly balances the inward pull of gravity. Push past that and you do not have a black hole anymore. You have a naked singularity, and those are forbidden by something called the cosmic censorship conjecture. Nobody has ever seen one. Most physicists believe they do not exist. Stellar black holes are also surprisingly common. Estimates suggest there are roughly 100 million stellar mass black holes in the Milky Way. That sounds like a lot. It is not. The galaxy contains somewhere between 200 and 400 billion stars. Black holes make up only a tiny fraction of the total. But that tiny fraction is enough to matter. Every black hole is a permanent resident. Once formed, a stellar black hole does not decay, it does not fade, it does not age. It just sits there, waiting, over trillions of years, long after the last star has burned out and the galaxy has gone dark. The black holes will still be there. They will be the last objects left, slowly evaporating through Hawking radiation on timescales longer than the current age of the universe. The formation of stellar black holes is also a window into the deaths of the first stars. The very first generation of stars, called Population 3 stars, formed from pure hydrogen and helium with no heavy elements at all. They were massive, probably hundreds of times the mass of the Sun, and they burned fast and died young. When they exploded, they scattered the first heavy elements into space. Some of them left black holes behind. Those black holes, if they survived to the present day, would be among the oldest objects in the universe. We have never confirmed one, but they should be out there somewhere, drifting through intergalactic space, older than any galaxy. Stellar black holes are the workhorses of the black hole family. They are not the biggest, they are not the strangest, but they are the most numerous and the most directly connected to the life cycles of stars. Every stellar black hole in the galaxy is a fossil, a relic of a star that died millions or billions of years ago, and they are still being born. Somewhere in the Milky Way right now, a massive star is running out of fuel. Its core is collapsing. In a few days or weeks it will explode, and when the light fades, there will be one more black hole added to the census. But stellar black holes are not the end of the story. They are just the beginning, because at the center of every large galaxy, including ours, there is something much bigger, something that did not form from a single star, something that weighs millions or billions of times more than the Sun. And it has been sitting there quiet and patient since the galaxy was young. But stellar black holes are not the end of the story. They are just the beginning, because at the center of every large galaxy, including ours, there is something much bigger, something that did not form from a single star, something that weighs millions or billions of times more than the Sun. And it has been sitting there quiet and patient since the galaxy was young. Our galaxy, the Milky Way, is home to roughly 400 billion stars. They are arranged in a flat disk with spiral arms curling outward from a bright central bulge. From our vantage point on Earth, sitting about 2/3 of the way out from the center on one of those spiral arms, the Milky Way looks like a river of light stretched across the summer sky. The ancient Greeks called it Galaxius Kyklos, the Milky Circle. We shortened it to galaxy. For most of human history, we did not know we were inside one. We did not know there were other galaxies. We thought the Milky Way was the entire universe. It is not. The Milky Way is just one galaxy among hundreds of billions. And at the center of ours, buried behind clouds of gas and dust so thick that visible light cannot penetrate them, there is a radio source. Astronomers call it Sagittarius A star. The name comes from its location in the constellation Sagittarius and the fact that it emits radio waves. The star notation is a quirk of astronomical naming conventions. It is not a star. It is a supermassive black hole weighing about 4 million times the mass of our Sun, and everything in the galaxy, including our solar system, is orbiting it. Sagittarius A star sits roughly 26,000 light-years from Earth. That is far enough that the black hole poses no danger to us. We are not falling in. We are orbiting, along with every other star in the galactic disk, in a slow, stately circle that takes about 225 million years to complete. The last time our solar system was at this point in its orbit, dinosaurs had not evolved yet. The next time we complete a lap, the Sun will be noticeably older, and the continents will have rearranged themselves into shapes no human would recognize. Galactic orbits are slow. From our perspective, the center of the Milky Way might as well be standing still, but it is not. The center is the most dynamic, violent, energetic region in the entire galaxy. The density of stars near the galactic core is so high that they are packed millions of times closer together than they are out here in the suburbs where we live. If Earth were located near the center, the night sky would not be black. It would be crowded with stars so bright they would cast shadows. The radiation environment would be lethal. And orbiting through all of that, closer to Sagittarius A star than we are to the Sun, are a handful of stars moving so fast that their orbits complete in a matter of years. These stars are the key. They are the reason we know Sagittarius A star is a black hole and not just a dense cluster of stars or some other exotic object. Astronomers have been tracking the motions of stars near the galactic center for decades, and the orbits tell a story that only makes sense if there is a single massive compact object sitting at the center pulling everything around it. The campaign to map those orbits began in the early 1990s when two teams, one led by Reinhard Genzel in Germany and one led by Andrea Ghez at UCLA, started using the world's most powerful telescopes to peer through the dust. Visible light does not make it through the gas clouds that blanket the galactic center, but infrared light does. Infrared wavelengths are longer and can slip past the dust grains that block shorter wavelengths. By observing in the infrared, Genzel and Ghez could see stars that no one had ever seen before, and they could watch those stars move. What they found was extraordinary. Some of the stars near the center were moving at speeds of thousands of kilometers per second. For comparison, our Sun orbits the galactic center at about 220 kilometers per second. These stars were moving more than 10 times faster. One star in particular, designated S2, became the focus of intense study. S2 is a bright blue star orbiting so close to Sagittarius A star that its orbit takes only 16 years. In galactic terms, that is a blink. Astronomers could watch it complete an entire lap in less than 2 decades. S2's orbit is highly elliptical. At its farthest point, it is about 16 light-hours from Sagittarius A star. At its closest approach, called periastron, it comes within about 14 billion kilometers of the center. That is less than the distance from the Sun to Neptune. And at that distance, the star is moving at nearly 3% of the speed of light. That is fast enough that relativistic effects, the time dilation and gravitational redshift predicted by Einstein's general relativity, become measurable. In 2018, S2 reached periastron. Telescopes around the world, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii, watched. The star's light was redshifted by the intense gravity of Sagittarius A star, exactly as general relativity predicted. The amount of redshift matched the equations to within the margin of error. It was one of the most precise tests of general relativity ever conducted in a strong gravitational field, and it confirmed something even more important. The object at the center of the Milky Way is not a cluster of stars. It is not a cloud of dark matter. It is a single compact object weighing about 4 million solar masses, packed into a region smaller than the orbit of Mercury. The only thing that fits that description is a black hole, a supermassive black hole. Supermassive black holes are not just scaled-up versions of stellar black holes. They are a different class of object entirely. Stellar black holes weigh a few times the mass of the Sun. Supermassive black holes weigh millions or billions of times the Sun's mass. The gap between them is enormous, and we still do not fully understand how supermassive black holes got so big. They did not form from a single star. No star is heavy enough to leave behind a million solar mass black hole when it dies. Supermassive black holes had to grow over time, either by eating gas and stars or by merging with other black holes. Both processes take time, billions of years in most cases, and yet supermassive black holes existed in the early universe, less than a billion years after the Big Bang. We have seen them. Quasars powered by billion solar mass black holes shine from an era when the universe was still an infant. How they grew so fast is one of the biggest unsolved problems in astrophysics. Sagittarius A star, by comparison, is not especially massive. At 4 million solar masses, it is small for a supermassive black hole. Some galaxies harbor black holes weighing tens of billions of solar masses, but Sagittarius A star is ours, and it is close enough to study in exquisite detail. The black hole itself is invisible, of course. It does not emit light, but the region around it is anything but dark. There is gas and dust spiraling inward, forming a structure called an accretion disk. The disk is not permanent. It flickers and changes as clumps of gas fall in and heat up. Some of that gas emits X-rays as it heats to millions of degrees. Some of it emits radio waves. Telescopes tuned to those wavelengths can see a faint glow marking the position of Sagittarius A star, even though the black hole itself is hidden. The X-ray emission is sporadic. Sagittarius A star flares up occasionally, brightening by a factor of 10 or more for a few hours before fading back to its usual dim state. Nobody knows exactly what triggers the flares. They might be caused by clumps of gas falling through the event horizon. They might be caused by magnetic fields in the accretion disk reconnecting and releasing energy. They might be caused by a star or a planet wandering too close and getting torn apart by tidal forces. The flares are unpredictable, which makes them hard to study. You cannot schedule telescope time around an event that might or might not happen on any given night, but the flares tell us something important. Sagittarius A star is feeding. Not efficiently, not continuously, but it is pulling in matter. Most of that matter does not make it to the event horizon. It radiates energy as it spirals inward and gets blown back out by the pressure of its own light. Only a small fraction actually crosses the horizon and adds to the black hole's mass. This is why Sagittarius A star is considered relatively quiet. It is accreting matter at a rate far below what the surrounding environment could supply. If it were feeding efficiently, it would be thousands or millions of times brighter. It would be an active galactic nucleus, a quasar, a blazing beacon visible across the universe. It is not. It is dim, almost invisible, detectable only because we are close enough to see the faint glow of gas heating up as it falls in. Compared to the supermassive black holes that power quasars and active galaxies, Sagittarius A star is asleep. It is not dead. It is just quiet. And that quietness is a bit of a puzzle. The galactic center is crowded with gas and stars. There should be plenty of material available for the black hole to eat. Why is it not eating? The answer seems to be that the gas near the galactic center is too hot. When gas is hot, it has a lot of random motion. That random motion, what physicists call thermal velocity, makes it harder for gravity to pull the gas inward. The gas wants to expand and escape rather than collapse and fall in. For a black hole to feed efficiently, the gas around it needs to be cool and dense so that gravity can win. Near Sagittarius A star, the gas is hot and turbulent. Most of it never makes it to the accretion disk. It just drifts around the center in chaotic orbits, occasionally getting flung out by interactions with stars or magnetic fields. There are also winds. The massive stars near the galactic center, dozens of them, are blowing powerful stellar winds into the surrounding space. Those winds collide and heat the gas even further, making it harder for the black hole to capture. The result is that Sagittarius A star is starving in the middle of a feast. The food is there, it is just too hot to eat. That might not always be the case. Galaxies are not static. Gas clouds move. Stars drift in and out of the galactic center. Every few thousand or million years, something large and dense, a molecular cloud or a star cluster, might wander close enough to Sagittarius A star to get captured. When that happens, the black hole lights up. For a brief period, geologically brief, it feeds efficiently and shines brightly. Then the fuel runs out and it fades back into silence. Some models suggest that Sagittarius A star goes through cycles of activity, flaring up every few 100,000 years when a fresh supply of gas becomes available, then dimming again when the supply dries up. We happen to be living in a quiet period. Lucky for us. If Sagittarius A star were active, life on Earth might not be possible. An actively feeding supermassive black hole does not just glow, it launches jets. Twin beams of matter and energy blasted outward at nearly the speed of light, perpendicular to the accretion disk. The jets from an active black hole can extend for hundreds of thousands of light years, punching through the surrounding gas and heating it to extreme temperatures. If Sagittarius A star were firing jets in our direction, the radiation would sterilize this side of the galaxy. We are lucky the black hole is pointed away from us, and we are lucky it is not feeding efficiently. A quiet black hole is a safe black hole. The radio emission from Sagittarius A star is constant but faint. The radio waves come from synchrotron radiation, produced when electrons spiral around magnetic field lines in the accretion disk. By measuring the radio spectrum and how it varies over time, astronomers can map the structure of the disk and estimate the magnetic field strength. The radio observations also provide a way to measure the size of the emission region, which gives an indirect estimate of the size of the event horizon. The event horizon of Sagittarius A star has a radius of about 12 million kilometers. That is roughly 17 times the radius of the Sun. Small compared to the size of our solar system, but enormous by any human standard. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. It was only the second image of a black hole ever made. The first had been M87 star, a supermassive black hole in a galaxy 55 million light-years away. Imaging Sagittarius A star was harder, even though it is much closer, because the accretion disk is smaller and changes faster. The gas around Sagittarius A star orbits in minutes to hours, whereas the gas around M87 star takes days. To get a clear image, the Event Horizon Telescope had to observe Sagittarius A star for hours and then combine thousands of snapshots into a single composite image. The result was a glowing orange ring with a dark shadow in the center. The ring is not the event horizon. It is the photon sphere, the region where light orbits the black hole before escaping or falling in. The shadow is the silhouette of the event horizon itself, backlit by the hot gas swirling around it. The image confirmed what decades of orbital measurements had already told us. There is a black hole at the center of the Milky Way. It weighs 4 million solar masses, and it is sitting right where the equations said it should be. The existence of supermassive black holes at the centers of galaxies is now considered one of the most robust findings in modern astronomy. Surveys have found supermassive black holes in nearly every large galaxy that has been studied in enough detail. Some are active, shining brightly as quasars or active galactic nuclei. Some are quiet, like Sagittarius A star, detectable only through the motions of stars or gas near the center. But they are there. Almost every galaxy has one. The bigger the galaxy, the bigger the black hole. There is a clear relationship between the mass of the central black hole and the mass of the galaxy's central bulge, the dense region of old stars surrounding the core. That relationship suggests that black holes and galaxies grow together, feeding off the same gas reservoirs, influencing each other's evolution in ways we are only beginning to understand. Sagittarius A star plays a role in shaping the Milky Way. Its gravity dominates the inner few light-years of the galaxy, where stars and gas orbit at extreme speeds. The tidal forces near the black hole are strong enough to tear apart stars that wander too close. When a star gets within a certain distance, called the tidal disruption radius, the difference in gravitational pull on the near side of the star compared to the far side becomes stronger than the star's own gravity. The star stretches, it elongates. Eventually it breaks apart, forming a long stream of gas that spirals into the black hole. This is called a tidal disruption event, and astronomers have observed them happening around supermassive black holes in other galaxies. We have not seen one at Sagittarius A star yet, but it is only a matter of time. Every few thousand or tens of thousands of years, a star should wander close enough to get shredded. The stars orbiting closest to Sagittarius A star, the S stars, are young. They are massive blue stars, the kind that only live for a few million years. That is strange because the galactic center is old. Most of the stars there are ancient red giants and smaller dim stars that have been around for billions of years. So where did the young S stars come from? They could not have formed in place. The tidal forces and radiation near Sagittarius A star would disrupt any gas cloud trying to collapse into a star. The leading theory is that the S stars formed farther out and then migrated inward, possibly as part of a star cluster that was disrupted by gravitational interactions. The stars were scattered, and a few ended up in tight orbits around the black hole. This process is called extreme mass segregation, and it is one of the ways galaxies concentrate their heaviest objects near the center. Sagittarius A star is also a probe of general relativity. The orbits of the S stars are so close to the black hole that they experience gravitational fields strong enough to produce measurable relativistic effects. In addition to the gravitational redshift observed during S2's close approach, astronomers have also measured the precession of its orbit. Precession is the slow rotation of the orbit's ellipse, a wobble caused by the curvature of spacetime near the black hole. Newtonian gravity predicts a small amount of precession due to the gravitational pull of other stars, but general relativity predicts an additional contribution from the black hole's gravity. The observed precession matches the relativistic prediction. It is another confirmation that Einstein was right, and it is a testament to how precisely we can now measure the motions of stars thousands of light-years away. The future of Sagittarius A star is tied to the future of the Milky Way. Galaxies do not stay isolated forever. They collide and merge. The Milky Way is currently on a collision course with the Andromeda Galaxy, a slightly larger spiral galaxy about 2.5 million light-years away. The two galaxies are approaching each other at about 100 kilometers per second. In about 4.5 billion years, they will collide. The collision will not be gentle. Stars will be flung into new orbits. Gas clouds will collide and ignite bursts of star formation, and the two supermassive black holes, Sagittarius A star and Andromeda's central black hole, which weighs roughly 100 million solar masses, will eventually spiral toward each other and merge. The merger will take millions of years. Black holes do not collide quickly. They orbit each other, losing energy by emitting gravitational waves, slowly spiraling closer. As they approach, the gravitational waves will grow stronger, rippling through space-time at frequencies detectable by future space-based gravitational wave observatories. When the two black holes finally merge, they will release a burst of gravitational wave energy powerful enough to be detected across the universe. The merged black hole will weigh roughly 104 million solar masses, making it one of the larger supermassive black holes in the local universe. And it will sit at the center of a new galaxy, a giant elliptical formed from the wreckage of the Milky Way and Andromeda. That future is billions of years away. For now, Sagittarius A star is quiet, patient, and ancient. It has been sitting at the center of the Milky Way for billions of years, pulling stars and gas into tight orbits, occasionally flaring as a clump of matter falls in, but mostly just waiting. It is the gravitational anchor of our galaxy, the point around which everything else revolves, and it is the closest supermassive black hole we have, close enough to image, close enough to study in extraordinary detail, close enough to test the most extreme predictions of general relativity in a real astrophysical system. But Sagittarius A star is not the only supermassive black hole we have imaged. In 2019, 3 years before the image of Sagittarius A star was released, the Event Horizon Telescope captured something even more dramatic. A black hole more than 1,000 times heavier, sitting at the center of a galaxy 55 million light-years away, surrounded by a glowing accretion disk and launching a jet that stretches across thousands of light-years. That black hole is called M87 star, and the image of it changed everything. But Sagittarius A star is not the only supermassive black hole we have imaged. In 2019, 3 years before the image of Sagittarius A star was released, the Event Horizon Telescope captured something even more dramatic. A black hole more than 1,000 times heavier, sitting at the center of a galaxy 55 million light-years away, surrounded by a glowing accretion disk and launching a jet that stretches across thousands of light-years. That black hole is called M87 star, and the image of it changed everything. M87 star sits at the heart of Messier 87, a giant elliptical galaxy in the constellation Virgo. Messier 87 is not a spiral like the Milky Way. It does not have graceful arms curling outward from a bright center. It is a bloated sphere of old stars, roughly 1 trillion of them, packed into a volume several times larger than our entire galaxy. The galaxy is ancient, formed from the mergers of dozens or hundreds of smaller galaxies over billions of years. And at its core, fed by all that chaos and collision, sits a black hole weighing 6.5 billion times the mass of the Sun. That is not a typo. 6.5 billion. For comparison, Sagittarius A star weighs 4 million solar masses. M87 star is more than 1,000 times heavier. Its event horizon has a diameter of roughly 38 billion kilometers. That is about 250 times the distance from the Earth to the Sun. You could fit our entire solar system inside the event horizon with room left over. Light, traveling at 300,000 kilometers per second, would take about a day and a half to cross from one side to the other. A day and a half to traverse the boundary of a single object, and that object is eating. Unlike Sagittarius A star, which is quiet and starving, M87 star is actively feeding. Gas is spiraling into the black hole at a steady rate, forming a bright accretion disk that shines across the electromagnetic spectrum. The disk glows in radio waves, infrared, visible light, ultraviolet, X-rays and gamma rays. It is one of the brightest objects in that region of the sky, outshining the trillion stars surrounding it. And it is launching a jet. The jet is what made M87 famous long before anyone imaged the black hole. Jets from supermassive black holes are among the most powerful phenomena in the universe. They are streams of matter and energy blasted outward at speeds approaching the speed of light, perpendicular to the accretion disk. The jet from M87 star extends for at least 5,000 light-years, punching through the galaxy and out into the surrounding intergalactic space. Observations with radio telescopes have traced the jet across more than 100,000 light-years. It does not stop at the edge of the galaxy. It keeps going, carving a channel through the hot gas that fills the space between galaxies. The jet is not a smooth beam. It is lumpy, knotted, variable. Bright spots appear and fade as clumps of matter race outward at relativistic speeds. The material in the jet is moving so fast that relativistic effects dominate. The light is beamed forward in the direction of motion, making the jet appear brighter and faster than it actually is. Physicists call this Doppler beaming, and it is one of the reasons jets from black holes are so luminous. The jet from M87 star is so bright in radio waves that it was one of the first extragalactic jets ever discovered, imaged in the 1950s by astronomers using some of the earliest radio telescopes. Nobody understood what they were looking at first. A thin stream of radio emissions stretching thousands of light-years from the center of a galaxy made no sense. Stars do not do that. Gas clouds do not do that. It took decades of theoretical work and better observations to realize that the jet was being powered by the supermassive black hole at the galaxy's core. The mechanism is still not fully understood, but the basic picture is clear. Matter spiraling into the black hole gets caught in powerful magnetic fields threading through the accretion disk. Those fields twist and amplify as the disk rotates. Some of the matter, instead of falling into the black hole, gets funneled along the magnetic field lines and accelerated outward. The energy comes from the rotation of the black hole itself, or from the gravitational potential energy of the infalling gas. Either way, the result is a focused beam of matter traveling at nearly the speed of light. The jet from M87 star does more than look impressive. It shapes the galaxy and the space around it. When the jet slams into the surrounding gas, it heats that gas to extreme temperatures and prevents it from cooling and collapsing into new stars. This is called feedback, and it is one of the ways supermassive black holes regulate the growth of their host galaxies. Without feedback, the gas in a massive galaxy like M87 would cool and collapse, forming new stars at a prodigious rate. The galaxy would keep growing, packing more and more stars into a smaller and smaller volume. But the black hole pushes back. The jet and the radiation from the accretion disk heat the gas, keeping it too hot to collapse. The result is that star formation shuts down. M87 is a dead galaxy. It is not making new stars. It is just sitting there, slowly aging, while the black hole at its center keeps the gas stirred up and prevents any new growth. This feedback process is one of the most important discoveries in galaxy evolution over the last few decades. Simulations of galaxy formation that do not include black hole feedback produce galaxies that are too massive and too densely packed with stars compared to what we observe. Add black holes and their jets into the simulation, and the galaxies come out looking much more like the real ones. Black holes, it turns out, are not just passengers in galaxies, they are regulators. They control how much gas can collapse into stars and how much stays hot and diffuse. The bigger the black hole, the more powerful the feedback, and the more tightly the black hole can control its galaxy's growth. M87 is a perfect example of this process in action. The galaxy is enormous, ancient, and almost completely devoid of star formation. The black hole has won. It has heated the surrounding gas to the point where no new stars can form, and it has been doing this for billions of years. The jet is the visible signature of that victory. Every time you see an image of the M87 jet, you are looking at a supermassive black hole actively suppressing the growth of its galaxy. But the jet is not the only reason M87 star is famous. In April of 2019, a team of more than 200 scientists working with the Event Horizon Telescope released the first direct image of a black hole. Not an artist's rendering, not a simulation, a real image reconstructed from radio telescope data showing the shadow of a black hole's event horizon. It was M87 star, and the image made headlines around the world. The image itself is simple, a glowing orange ring with a dark center. The ring is not perfectly circular. It is slightly brighter on the bottom than the top, an effect caused by the rotation of the accretion disk and the Doppler shift of the light coming from gas moving toward us versus gas moving away. The dark center is the shadow of the event horizon, not the event horizon itself, because light cannot escape from there, but the region where light orbits the black hole or falls in. The boundary between that shadow and the glowing ring is called the photon sphere. It is the closest stable orbit for light around a black hole. Inside the photon sphere, light cannot escape. It either spirals inward and crosses the event horizon, or it circles the black hole a few times before getting flung out. The image is not a photograph in the traditional sense. Black holes do not emit light. You cannot point a camera at one and take a picture. What the Event Horizon Telescope did was measure radio waves emitted by the hot gas surrounding the black hole, and then use that data to reconstruct an image of what the emission region looks like. The technique is called interferometry, and it is the same method radio astronomers have been using for decades to image distant objects with high resolution. But the Event Horizon Telescope took interferometry to an extreme. To image the event horizon of M87 star, which from Earth appears smaller than an orange sitting on the surface of the Moon, you need a telescope the size of the planet. Obviously, nobody can build a single telescope that large. So instead, astronomers built a network of telescopes scattered across the globe and linked them together. By synchronizing the observations with atomic clocks and combining the data later using supercomputers, they turned the entire Earth into one giant radio telescope. The technique is called Very Long Baseline Interferometry, VLBI for short, and it is one of the most technically challenging things astronomers have ever done. The Event Horizon Telescope is not a single observatory, it is a collaboration. 8 radio telescopes on 4 continents, from Hawaii to Chile to Spain to the South Pole, all observing the same target at the same time. Each telescope records the radio waves hitting its dish, along with a precise timestamp from an atomic clock. The data is stored on hard drives, physical hard drives, because the data rate is too high to transmit over the internet. The drives are shipped to a central processing facility, where supercomputers combine the signals. By comparing the arrival times of the radio waves at different telescopes, the software can calculate the phase and amplitude of the waves and reconstruct an image of the source. It is like piecing together a jigsaw puzzle where each telescope provides one piece of the picture. The challenge is that the black hole is small and far away. The resolution needed to image M87 star's event horizon is roughly 20 microarcseconds. A microarcsecond is 1/millionth of an arcsecond. An arcsecond is 1/3600th of a degree. To put that in perspective, 20 microarcseconds is the angular size of a golf ball on the Moon, as seen from Earth. No single telescope on Earth can achieve that resolution, but by combining telescopes separated by thousands of kilometers, the Event Horizon Telescope can. The farther apart the telescopes, the better the resolution. At radio wavelengths of about 1 millimeter, the Event Horizon Telescope has the resolution needed to see the shadow of M87 Nice Star's event horizon. The observations took place over several nights in April of 2017. The weather had to be clear at all 8 sites simultaneously. The telescopes had to be perfectly synchronized. The data had to be recorded without errors. Any mistake, any hardware failure, any cloud blocking the signal at even one telescope, and the entire observation would be compromised. It worked. The data was collected, the drives were shipped, and the analysis began. It took 2 years, 2 years of combining petabytes of data, testing different imaging algorithms, checking for errors, and making sure the result was real and not an artifact of the processing. In April of 2019, the team released the image, a glowing ring with a dark shadow in the center, the shadow of a black hole's event horizon. The reaction was immediate and global. The image appeared on the front page of newspapers around the world. It was shared millions of times on social media. It was compared to the Eye of Sauron from Lord of the Rings, which annoyed some astronomers but also captured the public imagination in a way few science results ever do. For the first time in history, humanity had seen a black hole, not inferred its existence from the motion of stars or the flicker of X-rays, but seen the shadow cast by the event horizon against the light of the surrounding gas. It was a landmark. A moment when something theoretical became observational, a moment when the universe showed us something we had only imagined. The image also confirmed general relativity. The size and shape of the shadow matched the predictions of Einstein's equations to within the margin of error. If general relativity were wrong, if gravity behaved differently in the extreme environment near a black hole, the shadow would have looked different. It would have been the wrong size or the wrong shape, or the brightness distribution would have been off. It was not. The shadow looked exactly the way the equations said it should look. The glowing ring was exactly where it should be. The asymmetry caused by Doppler shifting was exactly what the models predicted. General relativity once again passed the test. And this was not a weak field test like the orbit of Mercury or the bending of starlight during a solar eclipse. This was a strong field test, conducted in the most extreme gravitational environment we can observe. A black hole with 6.5 billion solar masses, where spacetime is curved so sharply that the equations are stretched to their limits, and they held. Heino Falke, one of the founding members of the Event Horizon Telescope collaboration, described the image as a photograph of a black hole silhouetted against light. The black hole itself is invisible. What we see is the light from the accretion disk, bent and focused by the black hole's gravity, surrounding a dark region where no light can escape. The shadow is larger than the event horizon, because light that passes close to the horizon gets pulled inward. The boundary of the shadow is not the boundary of the event horizon, it is the boundary of the region where light can no longer escape. That boundary, called the photon sphere, sits about 2.5 times farther from the center than the event horizon itself. So when you look at the image of M87 star, the dark circle in the middle is roughly 2.5 times wider than the actual event horizon. The glow around the shadow comes from the accretion disk. The disk is not uniform. It is turbulent, threaded with magnetic fields, heated to billions of degrees in some regions and cooler in others. The light we see is synchrotron radiation, emitted by electrons spiraling around magnetic field lines at relativistic speeds. The brightness varies depending on the density of the gas, the strength of the magnetic field, and the velocity of the material. The asymmetry in the image, the fact that the bottom of the ring is brighter than the top, comes from Doppler beaming. The gas in the accretion disk is orbiting the black hole at a significant fraction of the speed of light. Gas moving toward us appears brighter because its light is blue-shifted and beamed in our direction. Gas moving away from us appears dimmer because its light is red-shifted and beamed away. The result is that one side of the ring looks brighter than the other. By measuring the asymmetry, astronomers can infer the direction of rotation of the accretion disk. The disk around M87 star is rotating clockwise as seen from Earth. The image also tells us something about the spin of the black hole itself. A spinning black hole drags spacetime around with it, a process called frame dragging. The faster the black hole spins, the more spacetime gets twisted, and the closer the innermost stable orbit of the accretion disk sits to the event horizon. By measuring the size of the shadow and comparing it to models, astronomers can estimate the spin. The results suggest that M87 star is spinning, but not at the maximum rate. It is spinning moderately, somewhere between a non-rotating black hole and the fastest possible spin allowed by general relativity. That tells us something about how the black hole has been feeding. A black hole that has been steadily accreting gas from the same direction for billions of years should be spinning near the maximum rate. A black hole that has been fed by chaotic, randomly oriented inflows should be spinning more slowly. M87 star's moderate spin suggests that its feeding history has been a mix of the two, sometimes steady, sometimes chaotic. The Event Horizon Telescope did not stop with M87 star. The collaboration has been working to image other black holes, including Sagittarius A star. Imaging Sagittarius A star is harder because the accretion disk is smaller and changes faster. The gas around M87 star orbits over the course of days or weeks. The gas around Sagittarius A star orbits in minutes to hours. To get a clear image, the Event Horizon Telescope has to observe for many hours and then stitch together thousands of snapshots, each showing a slightly different configuration of the disk. The result, released in 2022, was a similar glowing ring with a dark shadow, but fuzzier and less symmetric because of the faster variability. Still, the image confirmed that Sagittarius A star is indeed a black hole and that its shadow matches the predictions of general relativity just as closely as M87 star's does. But M87 star remains the landmark. It was the first, and it was, in many ways, the easier target. The black hole is heavier, the accretion disk is larger, and the variability is slower. The image is cleaner, sharper, more iconic. When people think of a black hole image, they think of M87 star, that glowing orange ring, that dark shadow, that moment when the invisible became visible. The jet from M87 star also plays a role in the broader universe beyond the galaxy. The intergalactic medium, the thin, hot gas that fills the space between galaxies, is not empty. It contains a significant fraction of the universe's ordinary matter, and it is heated to temperatures of millions of degrees by the jets and winds from galaxies like M87. When the jet from M87 star plows into the intergalactic gas, it compresses and heats the gas, creating shock waves that ripple outward for hundreds of thousands of light years. Those shock waves can trigger or suppress star formation in nearby galaxies, depending on whether they compress the gas enough to make it collapse or heat it enough to prevent collapse. The jet from M87 star is not just affecting its own galaxy, it is affecting the entire cluster of galaxies surrounding it. M87 sits at the center of the Virgo cluster, a collection of roughly 2,000 galaxies. The jet from M87 star is shaping the environment of the entire cluster. Jets from supermassive black holes are also one of the main ways energy gets distributed throughout the universe. Stars produce energy through fusion and release it as light. Black holes produce energy by converting gravitational potential energy into radiation and kinetic energy in jets. Over the lifetime of the universe, supermassive black holes have pumped enormous amounts of energy into the intergalactic medium, preventing gas from cooling and collapsing into galaxies and regulating the overall rate of star formation. Without black holes and their jets, the universe would look very different. Galaxies would be more massive, more densely packed with stars, and the intergalactic medium would be cooler and denser. Black holes are not just objects sitting at the centers of galaxies. They are architects of cosmic structure. The image of M87 star is also a reminder of how much we have learned in a very short time. A century ago, black holes were not even a concept. General relativity was new, and the idea that space-time could curve so sharply that light could not escape was considered a mathematical oddity with no connection to the real universe. 50 years ago, black holes were theoretical predictions that most astronomers believed in but had never seen. 20 years ago, we had indirect evidence from X-ray binaries and the motions of stars near galactic centers, but no direct observation of an event horizon. And then in 2019, we saw one. We saw the shadow cast by the event horizon of a black hole 6.5 billion times the mass of the Sun, sitting 55 million light-years away. We turned the Earth into a telescope and captured the image. That is the speed at which science moves when the technology and the theory align. The Event Horizon Telescope is not done. The collaboration is planning to add more telescopes to the network, which will improve the resolution and allow them to make movies instead of single snapshots. Movies of the gas swirling around M87 star, falling through the event horizon, disappearing from view. Movies of Sagittarius A star, flaring as clumps of gas cross the horizon. Movies that will let us watch black holes feed in real time. The next generation of observations will also extend to shorter wavelengths, which will provide even higher resolution and allow astronomers to probe closer to the event horizon. The goal is to test general relativity in even more extreme conditions and to understand the physics of accretion disks and jets in unprecedented detail. M87 star will remain a central target. It is one of the closest supermassive black holes, one of the most massive and one of the brightest. It is also one of the best laboratories for studying black hole physics because the jet provides a direct observable connection between the black hole and the surrounding universe. Every observation of M87 star teaches us something new about how black holes feed, about how jets are launched, about how general relativity behaves in extreme gravitational fields, about how supermassive black holes shape galaxies and clusters, and the universe as a whole. But M87 star, as massive and impressive as it is not the largest black hole we have found, not even close. 6.5 billion solar masses is enormous. It dwarfs Sagittarius A star. It dwarfs every stellar mass black hole in the Milky Way. But there are black holes out there that make M87 star look small. Black holes so massive that they challenge our understanding of how black holes can grow. Black holes weighing not billions, but tens of billions of solar masses. Black holes that formed so early in the universe that they should not have had time to exist. And at the top of that list, sitting at the edge of the observable universe, is a monster that has been waiting for us since the beginning, Ton 618. But M87 star, as massive and impressive as it is not the largest black hole we have found, not even close. 6.5 billion solar masses is enormous. It dwarfs Sagittarius A star. It dwarfs every stellar mass black hole in the Milky Way. But there are black holes out there that make M87 star look small. Black holes so massive that they challenge our understanding of how black holes can grow. Black holes weighing not billions but tens of billions of solar masses. Black holes that formed so early in the universe that they should not have had time to exist. And at the top of that list, sitting at the edge of the observable universe, is a monster that has been waiting for us since the beginning. TOE N618. TOE N618 is a quasar. That word gets thrown around a lot, but it is worth stopping to explain what it actually means, because quasars are not just bright objects. They are the brightest, persistent objects in the universe. A quasar is the active core of a distant galaxy, powered by a supermassive black hole feeding so efficiently that the light from its accretion disk outshines every star in the galaxy combined, often by a factor of hundreds or thousands. From billions of light-years away, the galaxy disappears. All you see is the quasar, a single point of light so bright it looks like a star. That is where the name comes from. Quasi-stellar object, something that looks like a star but is not. TOE N618 is not just any quasar. It is a hyperluminous quasar, one of the brightest ever found. Its luminosity is estimated at roughly 140 trillion times the brightness of our Sun. 140 trillion. If you took every star in the Milky Way, all 400 billion of them, and added up their combined light output, TOE N618 would still outshine them by a factor of several hundred. One object, one black hole, brighter than hundreds of entire galaxies. That light has been traveling toward Earth for more than 10 billion years. We are seeing TOE N618 as it existed when the universe was only about 3 billion years old, less than a quarter of its current age. The light left TOE N618 before our solar system existed, before the Milky Way had finished assembling itself into the spiral galaxy we know today, before most of the stars you see in the night sky were born. And that light, after crossing more than 10 billion light-years of expanding space, is still bright enough to show up in our telescopes as one of the most luminous objects in the sky. The source of that light is the accretion disk. Gas spiraling into the black hole at the center of TOE N618 is being heated to millions of degrees by friction and compression. At those temperatures, the gas glows across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays. The disk is so hot and so luminous that the radiation pressure, the outward push of light itself, is strong enough to blow gas away from the black hole. This creates a tension. The black hole is trying to pull gas in. The light from the disk is trying to push gas out. The balance between those two forces determines how fast the black hole can feed. There is a limit to how fast a black hole can grow by eating gas. It is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who calculated it in the early 20th century. The Eddington limit is the point where the outward pressure of radiation exactly balances the inward pull of gravity. Feed a black hole faster than the Eddington limit, and the gas gets blown away before it can fall in. The black hole stops growing. The limit depends on the black hole's mass. The more massive the black hole, the higher the Eddington limit. A black hole feeding at the Eddington limit doubles its mass every few tens of millions of years. That sounds fast. It is not fast enough to explain TOE N618. The black hole at the center of TOE 618 weighs roughly 66 billion times the mass of the Sun. 66 billion. That is not a supermassive black hole in the usual sense. That is an ultramassive black hole. Some astronomers call it a hypermassive black hole. The terminology is not standardized, but the point is the same. This is not M87 star. This is not Sagittarius A star. This is something in a completely different weight class. M87 star weighs 6.5 billion solar masses. Ton 618 is 10 times heavier. Sagittarius A star weighs 4 million solar masses. Ton 618 is more than 16,000 times heavier. If you tried to build a scale model where Sagittarius A star was the size of a marble, Ton 618 would be the size of a house. The event horizon of Ton 618, the boundary beyond which nothing can escape, has a diameter of roughly 1,300 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. Pluto orbits at about 40 astronomical units. The event horizon of Ton 618 is more than 30 times farther out than Pluto's orbit. From edge to edge, the event horizon spans roughly 2,600 astronomical units. You could line up dozens of solar systems, Sun to Pluto to Sun to Pluto, across that diameter and still have room left over. Light traveling at 300,000 kilometers per second would take about 2 weeks to cross from one side to the other. 2 weeks for light to traverse the boundary of a single object. And this object, this 66 billion solar mass monster, existed when the universe was 3 billion years old. Run the math, and the timeline does not work. A black hole, feeding at the Eddington limit, starting from a stellar mass seed of, say, 10 solar masses, would take billions of years to reach even 1 million solar masses. To reach 1 billion solar masses, you need many billions of years. To reach 66 billion solar masses, you need more time than the universe has existed. There is no clean path from a collapsing star to Ton 618 in 3 billion years. The numbers do not close. So how did it get so big so fast? That is the central mystery. And it is not just Ton 618. TON 618 is the most massive example, but astronomers have found dozens of quasars in the early universe powered by black holes weighing billions of solar masses. All of them formed in the first billion years after the Big Bang. All of them are too heavy to have grown from stellar seeds in the time available. Something about the early universe allowed black holes to grow faster than they should have. Or the seeds they started from were much heavier than a single collapsing star, or both. The first possibility is that the black holes were feeding faster than the Eddington limit. This is called super-Eddington accretion, and it is not forbidden by physics. The Eddington limit assumes the accretion disk is thin and radiates efficiently. But if the disk is thick and bloated, some of the radiation can get trapped inside the disk and carried inward instead of escaping. The gas falls in faster. The black hole grows faster. The trade-off is that super-Eddington accretion is unstable. The disk puffs up. It becomes turbulent. It probably does not last for very long. But if the early universe had conditions that favored super-Eddington feeding, maybe in dense gas-rich environments where collisions and mergers were common, black holes could have grown much faster than the standard models predict. The second possibility is that the seeds were heavier. Most supermassive black holes are assumed to have grown from stellar mass black holes, the kind that form when massive stars collapse. Those seeds weigh 10 to 100 times the mass of the Sun. Start from there and you are fighting an uphill battle to reach billions of solar masses in a few 100 million years. But what if the seeds were heavier? What if the first black holes did not come from stars at all? What if they formed directly from the collapse of massive gas clouds in the early universe, skipping the stellar phase entirely? This idea is called direct collapse. In the chaotic conditions of the early universe, before the first stars had enriched the gas with heavy elements, Giant clouds of primordial hydrogen and helium could have collapsed under their own gravity. Normally, collapsing gas heats up and the pressure resists further collapse. But if the gas is very dense and very hot to begin with, and if there are no heavy elements to radiate away the heat, the collapse can run away. The cloud does not fragment into stars. It collapses into a single massive object. If the conditions are right, that object could be a black hole weighing tens of thousands or even hundreds of thousands of solar masses from the moment it forms. Start with a seed that heavy and the growth problem becomes much easier. 100,000 solar mass black hole feeding at the Eddington limit can reach 1 billion solar masses in a few 100 million years. Reach 10 billion solar masses in less than 1 billion years. The timeline fits. The catch is that direct collapse requires very specific conditions. The gas has to be metal-free, which is only true in the very early universe. The gas has to be irradiated by ultraviolet light from nearby stars, which heats it enough to prevent normal star formation, but not so much that the cloud disperses. And the gas cloud has to be massive and dense enough that gravity can overwhelm the pressure. Those conditions are rare, but maybe not rare enough. Maybe in the first few 100 million years after the Big Bang, direct collapse black holes were forming all over the place, and maybe 2N618 grew from one of them. The third possibility is mergers. Black holes do not just grow by eating gas, they also grow by colliding with other black holes. When two galaxies merge, their central black holes eventually spiral toward each other and merge into a single larger black hole. If the early universe was more chaotic than we think, with galaxies forming and merging at a much faster rate, black holes could have grown through repeated mergers. Start with a population of moderately massive black holes, say a few million solar masses each, and let them merge over and over again. Each merger adds mass. Within 1 billion years, you could build a black hole weighing tens of billions of solar masses. The challenge is that mergers take time. Two black holes do not collide quickly. They orbit each other, losing energy by emitting gravitational waves, slowly spiraling closer. The final merger might take millions of years depending on the masses and the distances involved. String together enough mergers fast enough, and you can grow a massive black hole. But it requires a very specific sequence of events and a very crowded environment. The most likely answer is some combination of all three. TON618 probably started from a heavier seed than a stellar mass black hole. It probably fed at super Eddington rates during certain periods when gas was abundant and the conditions were right. And it probably grew through mergers with other black holes as the host galaxy collided with neighbors. Each mechanism contributes. Together, they might be enough to explain how a black hole weighing 66 billion solar masses existed when the universe was only 3 billion years old. Might be. The truth is we do not know. TON618 remains a puzzle, a data point that does not fit cleanly into the models, a reminder that the early universe was doing things we have not figured out yet. One of the challenges in studying TON618 is that we cannot observe the black hole directly. We cannot image the event horizon the way the Event Horizon Telescope imaged M87 star and Sagittarius A star. TON618 is too far away. Its apparent size in the sky, the angle it subtends as seen from Earth, is far too small for any current telescope to resolve. The angular size of TON618's event horizon is roughly a few micro-arcseconds, which is smaller than the resolution of even the Event Horizon Telescope. To image TON618, you would need a telescope the size of the solar system. We do not have that. We will not have that for a very long time. So how do astronomers know how massive TON 618 is? They infer it, indirectly, from the light. The quasar shines because gas is falling into the black hole. The brightness of the quasar tells you how much energy is being released. The energy release depends on how much gas is falling in and how efficiently the accretion process converts gravitational energy into light. From the luminosity, you can estimate the accretion rate. From the accretion rate, assuming the black hole is feeding near the Eddington limit, you can estimate the mass. The mass estimate for TON 618 66 billion solar masses comes from this kind of reasoning. It is not a direct measurement, it is a model-based inference. The uncertainty is large. Some estimates put the mass closer to 40 billion solar masses, some put it higher. The exact number is less important than the order of magnitude. Whether it is 40 billion or 66 billion or 80 billion, the point is the same. This is an ultramassive black hole that should not have existed when it did. Another way to estimate the mass is to look at the motion of gas near the black hole. When gas orbits a massive object, the orbital speed depends on the mass of the object and the distance from it. Measure the speed and the distance, and you can calculate the mass. Astronomers can measure the speed by looking at the Doppler shift of emission lines in the quasar spectrum. Gas moving toward us is blue shifted. Gas moving away is red shifted. The width of the emission lines tells you how fast the gas is moving. The brightness of the lines tells you how dense the gas is and how far it is from the black hole. Combine those measurements and you get a mass estimate. This technique is called reverberation mapping, and it is one of the most reliable ways to weigh distant black holes. The results from reverberation mapping are consistent with the estimates from luminosity. TON 618 weighs somewhere in the range of 40 to 66 billion solar masses. Either way, it is one of the most massive black holes ever found. Some sources call it the most massive. That claim is debated because there are other candidates in the same mass range and the uncertainties are large. But TON 618 is always in the conversation. It is always near the top of the list, and it remains one of the best examples of an ultramassive black hole in the early universe. The existence of ultramassive black holes like TON 618 has implications for galaxy evolution. Black holes do not grow in isolation. They grow inside galaxies, and as they grow, they influence the galaxies around them. The radiation and jets from an actively feeding black hole heat the surrounding gas, preventing it from cooling and collapsing into new stars. This is the feedback process we talked about with M87 star. The bigger the black hole, the more powerful the feedback. An ultramassive black hole feeding at the rate TON 618 is feeding would pump enormous amounts of energy into its host galaxy. That energy would heat the gas to millions of degrees, blow it out of the galaxy entirely in some cases, and shut down star formation across large regions. The feedback from quasars like TON 618 is thought to be one of the main reasons why the most massive galaxies in the universe are not forming stars. The black holes grew so large and fed so efficiently that they effectively sterilized their host galaxies. The gas that would have formed new stars was either heated too much to collapse or blown out of the galaxy entirely. The result is a dead galaxy. No new stars, just old stars slowly aging and fading. The quasar eventually runs out of fuel as the gas supply dries up, and it fades into a quiet supermassive black hole like Sagittarius A star or M87 star. But in its active phase, the quasar was powerful enough to shape the entire evolution of the galaxy. TON 618 is still in its active phase, it is still feeding, it is still shining, and it is having a profound effect on its host galaxy. We cannot see the host galaxy directly because the quasar is so bright it drowns out the light from the stars. But models suggest the host galaxy is massive, probably weighing trillions of solar masses in stars and gas. The quasar is sitting at the center of that galaxy, pulling in gas at a prodigious rate and radiating energy at a rate that dwarfs the combined output of all the stars around it. The galaxy is being shaped by the black hole. The black hole, in turn, is being fed by the galaxy. The two are locked in a feedback loop that has been running for billions of years. There is also a broader implication for the cosmic web. The universe is not uniform. Matter is arranged in a web-like structure, with galaxies clustered along filaments and voids in between. The filaments are regions where gas and dark matter have collapsed under gravity, forming dense streams of matter that connect clusters of galaxies. The voids are regions where matter has been evacuated, leaving behind empty space. Quasars like TON 618 sit at the intersections of these filaments in the densest regions of the cosmic web. They are fed by the gas flowing along the filaments, and their radiation and jets, in turn, heat and redistribute that gas, affecting the structure of the web itself. The energy output from TON 618 is so high that it can influence the gas over scales of millions of light-years. The radiation ionizes the surrounding gas, stripping electrons from atoms and heating the gas to tens of thousands of degrees. The jets, if TON 618 has them, and we do not know for sure because the jets are hard to detect at such great distances, could extend for hundreds of thousands or even millions of light-years, carving channels through the intergalactic medium and redistributing matter across the cosmic web. The quasar is not just a local phenomenon. It is a cosmic-scale event, shaping the structure of the universe over regions larger than galaxy clusters. One of the surprising things about ultramassive black holes is that they may represent an upper limit to black hole growth. There is some theoretical work suggesting that black holes above a certain mass, somewhere in the range of 10 to 50 billion solar masses depending on the assumptions, start to experience diminishing returns. The radiation pressure from the accretion disk becomes so strong that it blows away most of the gas before it can fall in. The feedback becomes so powerful that it shuts off the gas supply entirely. The black hole stops growing, not because it runs out of time, but because it runs out of fuel. It becomes so massive that it effectively starves itself. TON 618 may be close to that limit. It may be one of the largest black holes that can exist in the universe given the laws of physics and the availability of gas in galaxies. If that is true, then TON 618 is not just a puzzle, it is a landmark, a signpost marking the upper boundary of black hole growth. Every black hole heavier than TON 618 that we find pushes that boundary a little higher and forces us to reconsider the models. Every black hole that matches TON 618 confirms that the limit, if it exists, is somewhere in this mass range. Either way, TON 618 is a benchmark, a reference point, a standard candle for the extremes of black hole physics. There is also something profoundly strange about the fact that TON 618 is so far away and so old. The light we see today left TON 618 more than 10 billion years ago. The black hole we are observing is not the black hole as it exists now. It is the black hole as it existed when the universe was 3 billion years old. Since then, 10 billion years have passed. The quasar has probably faded. The gas supply has probably run out. The black hole has probably gone quiet, settling into the kind of dormant state we see in Sagittarius A star and M87 star. It may have merged with other black holes if its host galaxy collided with neighbors. It may have gained or lost mass. It may have been ejected from its galaxy entirely by the recoil from a gravitational wave burst during a merger. We have no idea what Tone 618 looks like today because the light from today will not reach us for another 10 billion years. This is the strange reality of observing the distant universe. The farther you look, the further back in time you see. When you look at Tone 618, you are not looking at a black hole in the present, you are looking at a fossil, a snapshot of a black hole that existed when the universe was young. The object itself has moved on, it has evolved, it has changed. But the light carries the information from that ancient moment, and we are only now receiving it. Tone 618 is both real and gone, present and past, a ghost shining from the edge of the observable universe. The study of ultramassive black holes like Tone 618 is still in its early stages. We have found a few dozen candidates in the mass range above 10 billion solar masses. Some of them are quasars like Tone 618. Some of them are quiet black holes sitting in the centers of nearby massive galaxies, detected through the motions of stars or gas. Each new discovery refines our understanding of how black holes grow and what limits, if any, exist on their mass. Each new observation tests the models and pushes the boundaries of what we think is possible. Tone 618 remains the most extreme example we have found so far. It is not the only ultramassive black hole, but it is the most massive with the most robust mass estimate, and it is one of the most luminous quasars ever observed, which makes it a natural target for study. As telescopes improve and new techniques are developed, astronomers will continue to observe Tone 618 and objects like it, searching for clues about how they formed, how they grew, and what role they played in shaping the universe. There is also a philosophical dimension to Tone 618 that is hard to ignore. This is an object so massive, so distant, so ancient, that it challenges the limits of human comprehension. 66 billion times the mass of the Sun, an event horizon that takes light 2 weeks to cross. A luminosity equivalent to 140 trillion suns. Numbers like that stop meaning anything in the usual sense. They are too large, too extreme. The human brain did not evolve to grasp scales like this. We live on a planet 8,000 miles across, orbiting a star that weighs 2 times 10 to the power of 30 kilograms. We measure our lives in decades, our civilizations in centuries. Tone 618 operates on scales that dwarf everything we know. And yet we found it. We measured it. We calculated its mass and its distance and its luminosity. We looked across more than 10 billion light-years of space and saw the light from a black hole that was feeding when the universe itself was still figuring out how to make galaxies. That is what science does. It takes the incomprehensible and makes it measurable. It takes the invisible and makes it visible. It takes the ancient and makes it present. Tone 618 is a black hole. It is also a reminder that the universe is stranger, larger, and more extreme than anything we could have imagined if we had not gone out and looked for it. And the fact that we can study it, that we can weigh it and measure its light, and infer its properties from data collected by telescopes scattered across the Earth, is one of the most remarkable achievements in the history of science. But Tone 618 is not the end of the story. It is just the largest black hole we have found so far. And the study of black holes is not just about cataloging their masses and luminosities. It is about understanding what they are, what they do, and what they mean for the nature of reality itself. Because black holes are not just objects in the universe, they are cracks in the fabric of space-time. They are places where the laws of physics break down, and the rules we know stop applying, and they might, if some of the more speculative ideas in physics turn out to be correct, be doorways, passages to other regions of space-time, or to other universes entirely. That possibility, as strange as it sounds, is where the next part of this story leads. But Tone 618 is not the end of the story. It is just the largest black hole we have found so far. And the study of black holes is not just about cataloguing their masses and luminosities. It is about understanding what they are, what they do, and what they mean for the nature of reality itself. Because black holes are not just objects in the universe, they are cracks in the fabric of space-time. They are places where the laws of physics break down and the rules we know stop applying. And they might, if some of the more speculative ideas in physics turn out to be correct, be doorways, passages to other regions of space-time, or to other universes entirely. That possibility, as strange as it sounds, is where the next part of this story leads. Let's start with a problem that has bothered physicists for nearly 50 years. It is called the information paradox, and it sits at the intersection of quantum mechanics and general relativity like a splinter that nobody can pull out. The question is simple to state. What happens to information when it falls into a black hole? Not the matter itself, the information, the quantum state, the complete description of every particle, every field, every bit of data that crossed the event horizon. Does it vanish? Does it get destroyed? Or does it somehow survive? This matters because quantum mechanics has a rule: information cannot be destroyed, ever. It can be scrambled, encoded, hidden, spread across a system in ways that make it impossible to read, but it cannot be erased from the universe. The technical term is unitarity, and it is one of the foundational principles of quantum theory. If you know the exact quantum state of a system at one moment, the laws of physics allow you to calculate what the state was in the past or will be in the future. The information is conserved, always. Black holes seem to violate that rule. When matter falls through the event horizon, it disappears from view. The outside universe loses all access to the information that matter carried. The black hole itself, according to the no-hair theorem, only remembers three things: mass, spin, and electric charge. Everything else, the composition of the matter, the arrangement of atoms, the quantum states of particles, all of it gets erased. Or at least it looks that way from outside the horizon. The information seems to be gone. For decades, physicists tried to argue that this was not really a problem. Maybe the information is still there, just hidden behind the event horizon. You cannot see it, but it still exists. The problem is that black holes do not last forever. In 1974, Stephen Hawking published a paper showing that black holes emit radiation. The mechanism is quantum mechanical. Near the event horizon, pairs of particles and antiparticles pop into existence out of the vacuum, as they do everywhere in space. Normally, the pair annihilates almost immediately and nothing happens. But near the event horizon, one particle can fall in while the other escapes. From the outside, it looks like the black hole is radiating particles. The energy for those particles comes from the black hole's mass. Over time, the black hole loses mass. It shrinks. Eventually, it evaporates completely. Hawking radiation is extremely weak for large black holes. A black hole the mass of the Sun would radiate at a temperature of about 1/10,000,000th of a degree above absolute zero. That is far colder than the cosmic microwave background. The black hole would absorb more energy from the universe than it radiates. It would grow, not shrink. But smaller black holes radiate faster. A black hole the mass of a mountain would evaporate in seconds. A black hole the mass of the moon would take billions of years. There is a mass threshold, somewhere around 10 to the 12th kilograms, below which a black hole formed in the early universe would have evaporated by now. Hawking radiation is one of the most beautiful predictions in theoretical physics. It ties together quantum mechanics, general relativity, and thermodynamics in a single equation. It shows that black holes have a temperature and an entropy, that they are thermodynamic objects like everything else in the universe, and it implies that black holes are not eternal. Given enough time, they disappear. That is where the paradox sharpens. If the black hole evaporates completely, where does the information go? The radiation coming out of the black hole, at least in Hawking's original calculation, is completely random. It is thermal. It carries no information about what fell in. If you throw an encyclopedia into a black hole and wait for the black hole to evaporate, the radiation that comes out is just random particles with no memory of the encyclopedia's contents. The information is gone, destroyed. That is what Hawking's calculations seem to say. And if it is correct, quantum mechanics is wrong. Information can be destroyed. Unitarity fails. Physicists spent decades arguing about this. Some said the information is destroyed and we need to revise quantum mechanics. Some said the information escapes in the Hawking radiation, but in a way so scrambled that we cannot decode it. Some said the information is stored on the event horizon, encoded in tiny fluctuations in the horizon's geometry. Some said the paradox reveals that we do not understand black holes at all, that the interior is not what general relativity predicts, that something new and strange happens inside. Stephen Hawking himself changed his mind. He spent years arguing that information is destroyed. Then in 2004 he announced at a conference that he had been wrong. He conceded a bet he had made with another physicist, John Preskill, and gave Preskill a baseball encyclopedia as the prize. Hawking said he now believed the information escapes, but he did not have a complete explanation for how. The problem remained unsolved. The current leading idea is that information is encoded on the event horizon in a holographic way. The holographic principle, developed in the 1990s by physicists including Gerard Hooft and Leonard Susskind, suggests that all the information inside a region of space can be encoded on the boundary of that region. A black hole's event horizon is the boundary. The information about everything that fell in is not lost. It is imprinted on the surface of the horizon in patterns too subtle to measure with current technology. When the black hole evaporates, the information is released in the Hawking radiation, but encoded in correlations between particles that would take an impossibly detailed measurement to decode. The holographic principle goes further. It suggests that the entire universe might work this way. That everything we experience in three-dimensional space, all the matter, all the energy, all the structure, might be a projection of information encoded on a two-dimensional boundary. We would be living inside a hologram without realizing it. The idea sounds like science fiction. It is not. It is one of the most actively researched areas in theoretical physics. And it comes directly from trying to solve the black hole information paradox. The paradox is still not fully resolved. Physicists are making progress. New calculations using tools from string theory and quantum field theory suggest that information does escape, that unitarity is preserved, that quantum mechanics survives, but the details are murky. Nobody has a complete picture of how the information gets out or what the interior of an evaporating black hole looks like at the quantum level. The black hole information paradox remains one of the deepest unsolved problems in physics. And the fact that we are even asking the question, that we are trying to reconcile quantum mechanics with general relativity by studying what happens at the event horizon, shows how central black holes have become to our understanding of reality. Now let's go deeper, literally. What is inside a black hole? Not near the horizon, not in the accretion disk, inside, past the point of no return. In the region where general relativity says space-time becomes so warped that every path leads to the singularity. The honest answer is we do not know. Nobody has ever been inside a black hole. Nobody ever will, at least not, and lived to report back. Once you cross the event horizon, you are cut off from the outside universe. You cannot send a signal. You cannot turn around. You fall inward, and within a finite amount of your own time, you reach the singularity. What happens at the singularity is unknown because the equations of general relativity break down there. The curvature of space-time becomes infinite. Density diverges. The theory stops making predictions. Most physicists believe the singularity is not a real physical object. It is a signpost. A place where general relativity is telling us it no longer applies, that we need a better theory. Quantum gravity, whatever that turns out to be, should replace the singularity with something less catastrophic. Maybe space-time becomes discrete at small scales, breaking into tiny chunks that cannot be divided further. Maybe the singularity is smoothed out by quantum effects. Maybe the interior of the black hole connects to something else entirely. That last possibility is where things get strange. Some solutions to Einstein's equations allow for black holes that do not end in a singularity. They end in a tunnel, a bridge connecting one region of space-time to another. These bridges are called wormholes, and they have been part of theoretical physics since the 1930s. A wormhole is a shortcut through space-time. Enter on one side, exit on the other, bypassing the distance in between. In principle, you could use a wormhole to travel across the galaxy in seconds, or to travel backward in time, or to jump to a completely different universe. There is a catch, actually several. The first is that the wormholes predicted by general relativity are not stable. They collapse almost immediately unless you prop them open with something called exotic matter. Exotic matter is material with negative energy density, something that pushes space-time outward instead of pulling it inward. We have never seen exotic matter. We do not know if it exists. Quantum field theory allows for tiny amounts of negative energy in specific situations, but nowhere near enough to hold open a wormhole large enough for a person or even a particle to pass through. The second catch is that even if you could stabilize a wormhole, traversing it might not be survivable. The tidal forces near the throat of the wormhole, the narrowest part of the tunnel, could be strong enough to tear you apart. The radiation from quantum effects near the horizon could fry you before you made it through. And if the wormhole connects to a region of space-time with different physical conditions, the environment on the other side might be lethal. The third catch is that we have no evidence wormholes exist. NASA's Black Hole FAQ states plainly that wormholes are purely theoretical. They appear in the equations as possibilities, but nobody has found one. Nobody has detected the gravitational signature of a wormhole. Nobody has seen matter behaving in a way that would indicate a shortcut through space-time is present. The equations allow wormholes. The universe, as far as we can tell, does not. But the possibility has not been ruled out completely. Some physicists have suggested that the interiors of black holes might connect to white holes, hypothetical objects that are the time reverse of black holes. A white hole is a region of space-time where nothing can enter but everything can exit. Matter and light pour out of a white hole but cannot fall back in. White holes have never been observed. They may not be stable, but if they exist, and if the interior of a black hole connects to a white hole somewhere else, then a black hole is not an end, it is a passage. Another idea, even stranger, is that the interior of a black hole might contain an entire new universe. This idea comes from thinking carefully about what happens inside the event horizon. From the outside, an object falling into a black hole appears to slow down and freeze at the horizon. From the perspective of the object itself, it crosses the horizon in finite time and continues falling. The two perspectives are incompatible. They describe different realities. What if both are true? What if, from the outside, the black hole is a compact object with an event horizon, but from the inside, the space expands into a new region of space-time, a baby universe disconnected from our own? This is not idle speculation. It appears in serious theoretical work. Some models of quantum cosmology suggest that black holes could be the seeds of new universes. When a black hole forms, the interior does not collapse to a singularity. Instead, it undergoes a kind of quantum bounce, expanding into a new spacetime with its own physical laws. That new universe is causally disconnected from ours. We cannot see it. We cannot interact with it. But from the perspective of an observer inside the black hole, they would not see a singularity. They would see space expanding, matter spreading out, maybe even stars and galaxies forming. A new universe, born from the death of a star. If this is true, and nobody knows if it is, then every black hole in our universe is a doorway to another universe. And our universe might itself be the interior of a black hole in some larger parent universe. This is not proven. It is speculative. But it is mathematically consistent with what we know about general relativity and quantum mechanics, and it raises the unsettling possibility that the Big Bang, the beginning of our universe, was not a beginning at all. It was the interior of a collapsing star in a universe that existed before ours. We are living inside a black hole, and we would never know. Let's return to the holographic principle, because it deserves more attention. The idea is that the information content of any region of space is proportional not to the volume of that region, but to the area of its boundary. This is deeply counterintuitive. If you have a box, you would expect the amount of information inside the box to depend on how big the box is. More volume, more space for information. But the holographic principle says no. The information is encoded on the surface of the box. The interior is a projection of that surface. The three-dimensional space we experience is a hologram, a lower-dimensional encoding of information on a boundary. This idea came from studying black holes. A black hole's entropy, a measure of the amount of information it contains, is proportional to the area of its event horizon, not its volume. That was surprising. Entropy usually scales with volume. The fact that it scales with area for black holes suggested something fundamental about the nature of spacetime. Jacob Bekenstein proposed in the 1970s that black holes have entropy proportional to the area of their horizons. Stephen Hawking confirmed it by calculating the temperature of a black hole using quantum mechanics. The formula they derived, called the Bekenstein-Hawking entropy, is one of the most important results in theoretical physics. The holographic principle generalizes that result. If black holes encode information on their surfaces, maybe everything does. Maybe the entire universe is a hologram. This sounds absurd, but it has led to real progress in theoretical physics. The most famous example is the AD-S-CFT correspondence, a mathematical relationship between a theory of gravity in a higher dimensional space and a quantum field theory on the boundary of that space. The correspondence was discovered in the late 1990s by Juan Maldacena, and it has become one of the most powerful tools in string theory and quantum gravity research. The correspondence does not directly apply to our universe. The higher dimensional space in the correspondence is called anti-de Sitter space, which has a different geometry than the universe we observe. But the correspondence shows that the holographic principle is not just a vague idea. It is a concrete mathematical framework, and it suggests that gravity, spacetime, and geometry might not be fundamental. They might be emergent, projections of information encoded on a boundary. If the universe is holographic, what is the boundary? Where is the surface on which the information is encoded? One proposal is the cosmological horizon, the edge of the observable universe. Everything we see, every galaxy, every star, every black hole, is a projection of information encoded on that distant boundary. We are living inside a hologram, and the real information is written on a surface billions of light years away. The idea is difficult to test because we cannot access the boundary. But it makes predictions that can be tested indirectly, and physicists are working on those tests. The holographic principle also changes how we think about black holes. If the information about everything inside a black hole is encoded on its event horizon, then the interior might not exist in the way we think it does. The interior might be an emergent description, a way of organizing the information on the horizon. An observer falling into a black hole would experience an interior because that is how the information is decoded from their perspective. But an observer outside the black hole, watching from a distance, would see all the information encoded on the horizon. Both descriptions are valid. Both are real. They are just different ways of looking at the same underlying information. This sounds like philosophy. It is not. It is physics. The fact that two observers can have different but equally valid descriptions of the same system is central to relativity, both special and general. The holographic principle extends that idea. Different observers see different projections of the same information. Reality is not a single objective thing. It is a collection of perspectives, each encoding the same information in different ways. Black holes force us to take these ideas seriously. They are the laboratories where quantum mechanics and general relativity collide. They are the places where spacetime is so warped and gravity so strong that the approximations we use everywhere else break down. If we want to understand the fundamental nature of reality, of spacetime, of information, we have to understand black holes. And every time we think we understand them, they surprise us. Consider Hawking radiation again. When Hawking first calculated it, he thought the radiation was purely thermal, random, no information. But more recent work suggests the radiation is not random, it is correlated. Particles emitted early in the evaporation process are entangled with particles emitted later. The entanglement carries information. If you could measure every particle emitted by an evaporating black hole, and if you could decode the correlations between them, you could in principle reconstruct the information that fell in. The information is not lost, it is scrambled. The problem is that the scrambling is so extreme that reconstructing the information would require measurements far beyond anything we can do. You would need to catch every photon, every particle, emitted over billions or trillions of years. You would need to measure their quantum states with perfect precision, and you would need to solve an unimaginably complex decoding problem to untangle the information. It is theoretically possible. It is practically impossible. The information is there, but it is hidden so thoroughly that for all practical purposes it looks lost. This raises a question about the nature of physical laws. Is information really conserved if recovering it requires an impossible measurement? Or is there a difference between information that is hidden and information that is destroyed? Physicists argue about this. Some say the distinction matters. Some say it does not. The universe does not care whether we can perform the measurement. The information is either there or it is not. But the fact that we are even asking the question shows how black holes push us to the edge of what we understand. There is one more speculative idea worth discussing. Some physicists have proposed that black holes might be conscious, not in the human sense, not with thoughts or feelings or awareness, but in the sense that they process information. A black hole has entropy. It has a temperature. It evolves over time, emitting radiation and shrinking. All of those properties are associated with information processing. Some researchers have suggested that a black hole is, in a certain technical sense, a computer. It takes in information, stores it on the event horizon, and releases it through Hawking radiation. The event horizon is the memory, the radiation is the output. The black hole is computing something. What is it computing? Nobody knows. The idea is provocative but not widely accepted. Most physicists think it is a metaphor that should not be taken literally, but it highlights a deeper point. Black holes are not passive objects. They interact with the universe around them. They absorb matter and energy. They emit radiation. They have structure and dynamics and internal states. They are, in every meaningful sense, active participants in the physics of the cosmos. Now step back and look at the full picture. Black holes are regions where space-time is so warped that nothing can escape. They are predicted by general relativity, confirmed by observation, and found at the centers of most large galaxies. They range in mass from a few times the Sun to tens of billions of solar masses. They grow by eating gas and stars and by merging with other black holes. They emit radiation through quantum effects and will eventually evaporate if given enough time. They scramble information in ways that challenge our understanding of quantum mechanics. They might connect to other regions of space-time through wormholes. They might contain entire new universes inside their event horizons. They might encode information holographically on their surfaces. And studying them forces us to confront the deepest questions in physics. What is space-time? What is information? What are the fundamental laws that govern reality? Black holes are not just astronomical objects. They are probes of the universe's structure. Every prediction about black holes is a test of general relativity and quantum mechanics. Every observation of a black hole tells us something new about gravity, about the behavior of matter in extreme conditions, about the limits of our theories. And every unresolved paradox, every tension between prediction and observation points toward new physics, toward a deeper theory that unifies gravity and quantum mechanics, toward an understanding of space-time that goes beyond Einstein. We are not there yet. The theory of quantum gravity, whatever it turns out to be, is still incomplete. String theory, loop quantum gravity, and other approaches have made progress, but none of them have produced testable predictions that decisively confirm the theory. Black holes are one of the few places where we might find those predictions. The event horizon, the singularity, the Hawking radiation, all of these are places where quantum gravity should matter. If we can observe black holes with enough precision, if we can measure the subtle quantum effects near the horizon, we might finally see evidence of the theory that goes beyond general relativity. The Event Horizon Telescope is one step in that direction. Imaging the shadow of a black hole is a triumph, but it is only the beginning. Future telescopes will observe black holes in more detail, at higher resolutions, across more wavelengths. Gravitational wave detectors will catch more black hole mergers, measuring their masses and spins with greater precision. Space-based observatories will study black holes at X-ray and gamma-ray energies, probing the physics of accretion disks and jets. Each new observation is a piece of the puzzle. Each new measurement is a constraint on the theories. And every time we look at a black hole, we are looking at the edge of reality, the boundary where the known laws break down, the place where space-time becomes so extreme that the rules we have relied on for centuries stop applying. Black holes are not just objects to study, they are questions. What happens when matter collapses past every known limit? What happens at the singularity where the equations fail? What happens to information that crosses the event horizon? What happens inside the horizon where no light can return? We do not have all the answers. We may never have all the answers. But the fact that we are asking the questions, that we are building telescopes to observe black holes and writing equations to describe them and conducting experiments to test the theories, is one of the great achievements of the human mind. Black holes were once purely theoretical. Now they are real. We have seen them. We have imaged them. We have measured their masses and their spins and the way they bend light and time. We have listened to the gravitational waves they emit when they collide. We have watched stars orbit them at thousands of kilometers per second. We have traced the jets they launch across thousands of light years. We have found them in the early universe, heavier than they should be, challenging our models of how the cosmos evolved. Black holes are the most extreme objects in the universe. They are the densest, the darkest, the most powerful. They warp spacetime into shapes that defy intuition. They trap light itself. They scramble information in ways that challenge the foundations of quantum mechanics. They might be doorways to other regions of spacetime or to other universes entirely. They might encode the information of everything that falls into them on their event horizons in a holographic pattern. They might evaporate over unimaginable timescales, releasing the information back into the universe in a form so scrambled it looks random. They might be the seeds of new universes, born from the collapse of stars in older universes. They might be the key to understanding what spacetime actually is, whether it is fundamental or emergent, whether reality is a hologram projected from a distant boundary. We are living in an era where these questions are not just philosophical speculation, they are active areas of research. Physicists are building models, running simulations, analyzing data from telescopes and detectors scattered across the Earth and in space. Every year we learn something new. Every decade we refine the picture. The black holes we study today are not the black holes of Einstein's time, mathematical curiosities with no connection to observation. They are real objects with measured properties. And they are teaching us, slowly, what the universe is made of at its deepest level. TON 618, sitting 10 billion light-years away, weighing 66 billion times the mass of the Sun, shining with the light of 140 trillion stars, is one piece of that puzzle. Sagittarius A star, quiet and patient at the center of the Milky Way, is another. M87 star, imaged for the first time in 2019, surrounded by a glowing ring of light, is another. Every stellar mass black hole drifting through the galaxy, every intermediate mass black hole lurking in a star cluster, every primordial black hole that might be hiding in the dark matter halo, is part of the same story. A story about gravity, about space-time, about the limits of physical law. A story about how the universe works when you push it to its extremes. And the story is not over. We have only just begun to explore black holes in detail. The next generation of telescopes will see further, with higher resolution. The next generation of gravitational wave detectors will catch fainter signals from more distant mergers. The next generation of physicists will develop better theories, unifying quantum mechanics and general relativity in ways we have not imagined yet. And black holes will be at the center of that work, because black holes are where the universe reveals its deepest secrets. Where the known meets the unknown, where the measurable meets the incomprehensible, where the laws of physics are written in the geometry of space-time itself. Black holes are not just doors to reality. They are reality stripped down to its most essential form: mass, spin, gravity, information, nothing else. Everything that makes an object distinct, its composition, its history, its internal structure, gets erased at the event horizon. What remains is pure geometry, pure curvature. A dent in space-time so deep that not even light can climb out. And in studying that geometry, in measuring those dents, in tracing the paths of light and matter around them, we are learning what reality is made of. Not atoms, not particles, not fields, but information, structure, geometry, the shape of space-time itself. That is the final lesson of black holes. Reality is not made of things. It is made of relationships, of connections, of the way one part of the universe affects another. Black holes are the ultimate expression of that idea. They are regions where the relationships become so extreme, the connections so tight, that the usual descriptions break down. And in that breakdown, in that failure of the familiar laws, we catch a glimpse of something deeper, something more fundamental, something we are only beginning to understand. Are we living inside a black hole right now? The universe as we know it, with its galaxies and stars and planets, could be the interior of a black hole in some larger cosmos. From the outside, it would look like a compact object with an event horizon. From the inside, we see space expanding, matter spreading out, structure forming. The Big Bang would not be a beginning. It would be a transition, a bounce, a moment when the collapsing matter of a dying star in the parent universe underwent a quantum transformation and became the expanding space of our universe. We would never know. The two regions are causally disconnected. No signal can pass from one to the other. The boundary is absolute. This is speculation. It is not proven, but it is consistent with the equations, and it forces a question. If our universe could be the interior of a black hole in a larger universe, and if every black hole in our universe could contain a new universe inside it, then how many layers are there? How many universes stacked inside universes, each one the interior of a black hole in the layer above? The question has no answer. It might not even have meaning. But it is the kind of question black holes force us to ask. And the fact that we can ask it, that we can follow the equations to their logical conclusions and confront the implications, is part of what makes black holes so fascinating. Black holes are not just objects in space. They are challenges to our understanding. They are invitations to think more deeply, to question more carefully, to push the boundaries of what we know. Every black hole we observe is a data point. Every merger we detect is a test. Every image we capture is a step toward a more complete picture of how the universe works. And that picture, when we finally see it clearly, will be stranger and more beautiful than anything we imagined. So here we are, standing on a small rock orbiting an unremarkable star in the outer arm of a spiral galaxy, staring across billions of light-years of space at objects so extreme that they bend the very fabric of reality. Black holes, invisible monuments to the power of gravity, doorways to questions we barely know how to ask. We have traveled from the smallest, the primordial seeds that might have formed in the first second after the Big Bang, to the largest, Ton 618, a monster weighing 66 billion times the mass of our Sun, shining from an era when the universe was still a child. We have seen stellar black holes born in the violent deaths of massive stars, scattering the elements that make up everything we are. We have traced the orbits of stars around Sagittarius A star, watched them move so fast that time itself slows near the center of our galaxy. We have stared at the glowing ring around M87 star, the first image of a black hole's shadow, proof that the invisible can be made visible. And we have confronted the paradoxes, the information that might be encoded on event horizons, the singularities where the equations break, the possibility that every black hole contains a universe, and that our universe might be the interior of a black hole in some larger cosmos we will never see. Black holes are not just objects, they are questions written in the geometry of space-time. What is information? What is reality? What happens when the known laws fail? And the most unsettling question of all, the one we cannot yet answer but cannot stop asking. If the universe can build something as extreme as a black hole, if it can crush matter into a point so dense that space-time itself